Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Imagine yourself lying on a soft meadow on a clear night, far from any city lights. The air is cool against your skin, carrying the faint scent of grass. Above you, the sky is a black, velvet dome sprinkled with countless stars. The Milky Way arches overhead, a pale river of starlight. In this quiet moment, you feel deeply connected to the cosmos. The same space that stretches between those stars also surrounds you. A gentle breeze brushes your cheek. It moves through the night and through the space around you, here on Earth. As you gaze upward in comfortable silence, more and more pinpoints of light emerge, a glittering mosaic against eternity. You realize that when you look at these stars, you are literally looking back in time. Their light has traveled for hundreds or thousands of years to reach your eyes tonight. Some of those stars may have already lived out their lives and vanished, yet their glow still journeys onward through the dark to greet you here and now. You feel the solid earth beneath you and know that it too is suspended in that great darkness, a small, warm world afloat in an ocean of space. Yet you are not afraid. The darkness above feels inviting, almost comforting, like a vast shelter. The endless sky, rather than making you feel insignificant, fills you with peace and wonder. In the silence, you sense with gentle certainty that you are a part of this grand universe. The starlight that falls on your skin, the space that cradles your body, the photons entering your eyes, all of it binds you to the cosmos. You close your eyes for a moment. Behind your eyelids, the after-image of the stars dances in little sparkles. You take a slow breath in, and as you exhale, you let any tension flow out of you and into the vastness around. There is room for all of it to dissolve. There is room for everything in space. The universe is so wide and forgiving that your own cares begin to feel lighter, quieter, soothed by the infinite calm. Now, in that spirit of tranquility, let us embark on a journey into space itself. The space around us, the space within us, the space that is the foundation of all things. We begin where we are, in stillness, in the darkness, in the quiet. The night is profound and motionless. Above, the stars shine as tiny islands of light in a vast sea of black. Space stretches endlessly between and beyond them. This scene feels serene and timeless. Nothing stirs. No breeze now, no sound at all, only a gentle hush, the natural silence of a cosmos at rest. It is as though time itself has paused. You can almost feel the depth of this silence, a soft, velvety silence that blankets everything. The emptiness around you seems to embrace you with a subtle, invisible presence. For ages, we humans looked at the night sky and found it peaceful, but also mysterious. What is this blackness between the stars? We used to think it was nothing, an empty void, an infinite vacancy. People spoke of the void and the vacuum as if it were a true nothingness. We even doubted whether a true vacuum could exist at all. Ancient philosophers imagined that space must be filled with something. Aristotle believed nature abhorred a vacuum. Later, scientists in the 19th century hypothesized an invisible ether filling space to carry light across the emptiness. But experiments showed no such ether was needed. Light moves through empty space itself. This was a remarkable discovery. The void can carry light, as if emptiness has its own solidity. It hinted even then that space is not simply an inert backdrop. For a long time, though, the common view of space remained that it was a passive emptiness, a gargantuan container in which the objects of the universe, planets, stars, galaxies, are scattered. We pictured space as a stage and the stars as actors upon it, with no real influence from the stage itself. If you removed all the actors, the stage would just sit there, blank and silent. We imagined that if you took all matter away, you'd be left with pure nothing, an absolute void, infinite and eternal. Over time, however, our understanding evolved dramatically. We learned that space is far from nothing. That black backdrop, that stillness and silence, is deceptive. Space has properties, a structure, a dynamic of its own. In the past century, every new discovery has reinforced this truth. Space can bend. Space can carry light and soundless vibrations. Space can stretch. It can even boil at the tiniest scales, flickering with unseen energy. What we once thought of as an empty stage is more like a participant in the cosmic play. Tonight, as you float in this quiet moment, the darkness around you is not dead or inert. It is the very fabric that connects and supports all things. Let's explore this step by step, gently and thoroughly, starting with one of the most profound revelations, that space and gravity are intimately linked. Beneath you, the Earth's mass is pulling you down, or rather, it's warping the space under your body so that down is the direction you naturally fall. Above you, the moon is held in its orbit by the shape of space around Earth. This understanding comes from Einstein's great insight in the early 20th century. Gravity is not a mysterious force acting across empty distance, but a feature of space and time itself. Mass and energy tell space how to curve, and the curvature of space tells objects how to move. In essence, matter sculpts space, creating valleys and hills in the fabric of space-time, and objects simply roll along those curves. What you feel as gravity, the weight on your back as you lie in the grass, or the pressure of your body against your bed, is actually space itself pushing you downward, guiding you along the curved lines it has formed around the Earth. To visualize this, imagine space as a vast elastic sheet spread out under the stars. If you place a heavy object on that sheet, say a bowling ball to represent a star or planet, the sheet will dimple, sagging inward around the weight. Now, if you roll a marble nearby, representing a smaller object like a planet, the marble will no longer travel in a straight line. It will spiral around the bowling ball, caught in the curve. In reality, Earth orbits the Sun because the Sun's mass curves the space around it, creating a sort of well that Earth is rolling around. Earth thinks it's moving in a straight line, and indeed it is, locally, but space itself is curved, so straight for Earth is actually a loop around the Sun. There is no gravitational force pulling Earth in a literal sense. Earth is simply following the path allowed by the curved space, like a ball rolling around a curved bowl. All planets, all moons, all orbiting bodies are doing the same. They are not tethered by invisible strings. They are skating along the contoured roads of space. Right now, as you lie still, you are held to the ground by this phenomenon. The mass of the Earth has curved space under you such that down points toward Earth's center. Your body presses into the ground because space is telling you to move that way. The ground pushes back and holds you up. Space does this quietly and continuously. You feel the effect as weight, but really, it is space-time gently urging you along a curved path that the solid Earth prevents you from taking. If Earth were not here, that curvature would extend unopposed. You would fall freely along a path through space toward where Earth's center was. All of this happens with no sound and no drama. Space does its work quietly. In essence, what we experience as gravity is the shape of space around us. Matter, like the Earth beneath you, tells space-time how to curve, and that curved space-time tells matter how to move. Gravity is not something that reaches out through space. Gravity is space. The stillness around you, in fact, is full of these invisible curves and subtle depressions wherever there is mass nearby. If you could see the geometry of space, You'd see gentle indentations around every tree, for even small objects curve space a tiny bit. Deeper wells around the mountains, and a huge well under your body, reaching to Earth's core. But space does its job so smoothly that you don't notice anything odd. You just stay attached to Earth as naturally as a leaf rests on the ground. This idea also means that when a massive object moves, it can create ripples in the fabric of space. Much like a stone dropped in a pond sends out waves on the water. Imagine two massive stars circling each other rapidly, or better yet, two black holes, extremely dense objects, spiraling together. They disturb the space-time around them so much that waves of curvature spread outwards. These are called gravitational waves, literal ripples of space traveling at the speed of light, washing through the cosmos. For a long time, we weren't sure these ripples really existed, but in recent years, scientists built instruments so sensitive that they could feel space-time tremble. When two distant black holes collided and merged, in a galaxy billions of light years away, our detectors on Earth quivered ever so slightly. Space itself stretched and squashed by a tiny amount, far smaller than an atom, as the gravitational wave passed through. We heard the universe whisper through space-time. It was as if the stillness briefly sang a faint melody. Think about that. We built a device that can sense the movement of space from events that happened billions of years ago in far-off corners of the universe. When we detected those waves, it confirmed that space-time is not just an abstract idea. It's a real, physical fabric that can carry vibrations. Space can ring like a cosmic bell, even though we cannot hear it with our ears. In September 2015, when those two black holes merged, the fabric of space around Earth oscillated subtly, and our instruments recorded the telltale chirp. It was a triumph of human curiosity and a profound validation of the idea that emptiness has structure. The silence of space isn't absolute. If you have the right ears, space can indeed be heard. What an elegant picture, space as an ever-present elastic medium, carrying both the weight of stars and the whispers of their collisions. In summary, matter tells space-time how to curve, and space-time tells matter how to move. Gravity is not a pull through some void. It is the gentle guidance of objects along the contours of space-time. All of this, the Earth holding you, the Moon orbiting Earth, Earth orbiting the Sun orbiting our galaxy's center, is happening because space itself is shaped by mass and energy. Our everyday experience of weight is actually our intimate connection to the shape of space. So, from the stillness of space arises what seems to be a force, but space has more surprises. We've talked about space's shape. Let's now consider its unity with time. When Einstein described gravity as the curvature of space-time, he was saying something equally profound about time. That time is woven into the very fabric of space. Out in this quiet night, space and time seem separate. You can point in directions, you feel time passing. But experiments and theories show that they are inextricably linked. If you move fast or sit in a strong gravitational field, your experience of time changes relative to someone elsewhere. Space and time together form a four-dimensional weave, and gravity is the bending of that weave. Consider that the passage of time on the surface of Earth is slightly slower than time far out in space, because Earth's mass not only curves space, but also warps time. A clock on a mountain, where gravity is a tad weaker, ticks a little faster than a clock at sea level. Likewise, a clock on a fast-moving spaceship will tick slower than one on Earth. This isn't science fiction. We've measured it with precise atomic clocks. Even the GPS satellites in orbit must correct for time running faster up there. Weaker gravity, so faster time, compared to ground. Otherwise, their positioning would drift. What we find is that space and time adjust together. If space is squeezed or stretched, time is also altered. They are two aspects of a single entity, space-time. Think of space-time as a fabric with both spatial threads and temporal threads interwoven. You cannot disturb one without disturbing the other. When the sun's mass curves space-time, not only does space get warped, but time runs a bit slower near the sun compared to far away. An astronaut near a massive object ages a bit less quickly than one floating in weaker gravity. This is called gravitational time dilation. Similarly, if you travel at a speed close to light, time for you will slow relative to those you left behind. There is a famous thought experiment. Imagine twins, and one goes on a near light-speed journey to a distant star while the other stays on Earth. If the traveling twin returns after what she feels was perhaps a few years, she might find decades or more have passed on Earth. Her clock and body experience time more slowly due to her rapid motion through space-time. This isn't just a story, it's a real effect, verified by many experiments with particles and precise clocks. All of this tells us that space and time are not the separate, absolute backgrounds we once assumed. There is no universal time ticking the same for everyone, regardless of their state of motion or gravity. Instead, every observer has their own passage of time, depending on how they move through space and how space is curved where they are. Two people reunited after following different paths through space-time will have experienced different durations. What an astonishing reality. Time itself is elastic, flexible, personal. So here, under the stars, when you consider a moment of time and a stretch of space, realize they are part of one four-dimensional continuum. Here and now are bound together. You cannot point to a location in space without also specifying the moment in time. Everything that happens in space-time. The unity of space and time frames all experience. Right now, your heartbeat and the position of the moon both have coordinates in space-time, and gravity is the geometry of that space-time linking the two. Space and time are fused like two threads of a single fabric. Move fast through space, and you skew your passage through time. Stand in strong gravity, and time for you will run a bit slower than for someone far away. This interplay might sound complex, but think of it this way. Space alone isn't the full stage, and time alone isn't either. Rather, events unfold in space-time. If you try to separate them, you lose part of the picture. Even this peaceful moment has a space-time coordinate. You, here and now, under the night sky. As you lie there, time flows a tad differently than it would if you were orbiting the Earth or sitting on the moon, because the gravity and motion differ. The differences are small but real. Space-time enfolds you, ensuring that your now and here are connected into the grand tapestry of cause and effect that makes up reality. The important takeaway is, space and time are one fabric, and gravity is the bending of that fabric. The stillness you feel includes both space and time quietly doing their work. There is a timeless quality to this night because space and time together create that sensation. In this eternal present, you are embraced by space-time, which gently carries you along the stream of time while holding you in the structure of space. We have journeyed outward to see that what we thought was emptiness actually shapes the cosmos, and journeyed inward to see time intertwined with space. But the rabbit hole goes deeper. We must now explore the nature of space at the smallest scales, far smaller than a grain of sand, smaller than an atom, where an entirely new picture emerges. One might expect that if you zoom into space closely enough, you would eventually find absolute stillness and uniformity, perhaps even true nothingness. But our current understanding, through the lens of quantum physics, says otherwise. On extremely tiny scales, space is anything but smooth and still. It is frothing and fluctuating, buzzing with ephemeral activity. Physicist John Wheeler poetically called this the quantum foam. To grasp this, imagine shrinking yourself down beyond the microscopic, beyond the level of atoms, to a realm billions of times smaller. If you could stand there, if the word stand even makes sense at that scale, the tranquil emptiness you perceive at our scale would vanish. Instead, you'd witness space seething with spontaneous eruptions of energy. Particles would blink in and out of existence like fleeting sparks. Distances and directions would blur as uncertainty reigns. In quantum physics, even what we call a perfect vacuum, completely devoid of matter and cooled down to remove all heat, is not truly empty. There is a fundamental jitter that cannot be removed. This is because the laws of quantum mechanics tell us that certain pairs of physical properties, like energy and time, or position and momentum, cannot both be known with infinite precision. There is a built-in uncertainty, and because of it, a vacuum cannot have exactly zero energy for all time. If it did, we'd know both its energy, zero, and that it stays that way, no fluctuation, forbidden by quantum rules. Instead, the vacuum seethes with what we call zero-point energy, a baseline, irreducible energy. What does this mean in practice? It means that empty space is constantly witnessing tiny particles flickering into being from nothing, then vanishing almost immediately. These are often called virtual particles. For example, a particle of light, a photon, might momentarily pop into existence, along with a counterpart, perhaps an electron-positron pair, borrowing energy from the vacuum for a brief instant. They appear, exist ever so briefly, and then annihilate each other, paying back the energy. All of this happens on timescales and distances so small we normally have no way to detect it directly. But it's happening everywhere, all the time. The space around you, between you and the next breath of air, between the electrons and nuclei in your body, between the Earth and Moon, is awash in these quantum fluctuations. On the scale of the unimaginably small, much smaller than an atom's nucleus, space-time would not look like a smooth sheet. It would look like a turbulent ocean surface in a storm, full of random waves, bubbles, and wrinkles, hence quantum foam. One moment, a bit of space might have slightly higher energy, sprouting a virtual particle-antiparticle pair. An instant later they collide and disappear, leaving a slight vibration of energy that then might spawn another pair elsewhere. Space at that level is a riot of spontaneous activity, an invisible, high-speed flickering that averages out to a seemingly smooth, stable whole at larger scales. We've even observed tangible effects of this quantum vacuum. If you place two metal plates extremely close together in a vacuum, just a few nanometers apart, they will experience a tiny force pushing them toward each other. This is the Casimir effect, and it happens because the quantum foam between the plates is slightly different from the foam outside. Certain virtual particle wavelengths can't exist in the narrow gap, so there is a tiny imbalance, fewer electromagnetic modes between the plates than outside. The result is a subtle pressure that nudges the plates together. In essence, the empty space between the plates has less quantum activity than the space outside, causing them to be pushed inward by the more energetic fluctuations outside. It's a small force. You'd need sensitive instruments to measure it, but it's real and has been observed. It's as if the vacuum between the plates is not nothing. It exerts a gentle push. This is a direct demonstration that empty space is never truly empty. The vacuum is alive with energy and possibility. In particle physics experiments, we also see clues of the quantum vacuum. For instance, empty space can briefly lend energy for the creation of particle pairs that affect processes like nuclear decay. The very fact that protons and neutrons inside atomic nuclei can change forms via quantum fluctuations involving ghostly particles is tied to vacuum activity. Even the stability of atoms and the patterns of atomic spectra bear the imprint of zero-point energy. So, as incredible as it sounds, the takeaway is that emptiness is not truly empty. It's an active medium. The stillness we perceive is actually a frenetic dance at microscopic scales. The vacuum is constantly borrowing energy here, giving it back there, in accordance with quantum uncertainty, Put poetically, even when nature whispers hush, there remains an undercurrent of subtle noise, a quiet fizz of existence and annihilation on the tiniest scales. The concept of nothingness has been forever changed by this discovery. Empty space is a cauldron of potential, a field of fields, a stage for ceaseless miniature drama. If you were to shrink down into that realm, as a moment's imagination, since physically we cannot, you might see space flicker with tiny flashes, the foam that Wheeler described. It wouldn't be placid or uniform, it would be dynamic and random. The notion of a sharply defined point in space might lose meaning, blurred by these fluctuations. We sometimes say space-time becomes quantum foam at the Planck length, about 1035 meters, far smaller than any particle. At that scale, the smooth geometry of space-time breaks down into something probabilistic and fluctuating. Let's take a different kind of imaginative journey to appreciate this. Inward, into the fabric of matter and space inside you. Envision shrinking yourself, as we did under the stars, but now not in distance outwards, rather in size. You diminish down past the scale of dust mites, past cells and their nuclei, past even viruses and DNA molecules. Now you are smaller than an atom. Ahead of you floats a single atom of carbon from your body. It appears enormous from your current perspective. You approach it like a tiny spaceship nearing a planet. The atom consists of a blurry sphere, that is the cloud of electrons orbiting the nucleus. As you draw closer, this cloud is mostly transparent. You realize the electrons are tiny points moving so fast, they form a diffuse shell. You dive through this wispy shell of electron probability and find yourself in the interior of the atom. Suddenly, you are in what seems like a vast cavern. It feels eerily similar to drifting in space between stars. It is dark and almost empty. You might even see a faint glow of energy fluctuations around. The quantum foam flickers here too. For a moment, it's as if you're floating in a miniature version of outer space, a huge volume with almost nothing in it. Ahead, after some distance, you see a tiny but brilliant object, the atomic nucleus. You move toward it. What before was the immense atom is now mostly behind you. All that's left ahead is that nucleus, a cluster of protons and neutrons tightly clumped. It's small, incredibly small. If the whole atom were a cathedral, the nucleus would be like a single grain of sand at its center, and yet, that grain of sand holds almost all the mass. You come right up to the nucleus. It's made of particles bound together, busy with internal motions, but you cannot linger. At this scale, forces are intense. You decide to zoom back out. When you return to human scale, you carry with you a profound appreciation. Inside every atom in your body, between the electrons and the nucleus, there are enormous stretches of empty space. In fact, nearly all of the volume of each atom is empty. The solidity of your body, of the ground, of this meadow, it's an illusion created by the electromagnetic forces of electrons repelling each other at those tiny distances. No two atoms ever truly touch in a physical sense. Their electron clouds push against each other first. Matter is a scaffold built on emptiness. It is astonishing. All the solid things we see around us are about 99% empty space. If one could magically remove all the empty space within the atoms of your body, compressing the electrons into the nuclei, you would shrink to a microscopic speck, smaller than a pinhead, yet you'd weigh the same as you do now. By some estimates, if we removed all the empty space from all the atoms of all humans on Earth, the entire human race could fit into a volume the size of a sugar cube. It sounds impossible, but it's because atoms are so vast compared to their tiny nuclei. Nature itself offers a demonstration. In neutron stars, the remnants of large stars, gravity crushes atoms so hard that electrons and protons merge, eliminating that atomic emptiness. A single teaspoon of neutron star material can weigh billions of tons. That's how much stuff was hiding in the empty space of atoms. When that space is removed, matter's true density shows. Fortunately, here on Earth, our matter stays spacious, our atoms intact with their generous voids inside. Take a moment to let that sink in. Solidity is an illusion. When we say an object, a rock, a chair, your own body, is solid, we're talking about the collective sense of touch that arises from trillions of atoms whose electrons resist being pushed into the empty space of one another. It is like a lattice of charged particles, and their mutual repulsion gives structure and firmness. But the structure is mostly empty space. We and the world we live in are made of a whole lot of nothing. It's a humbling realization. You are a being composed almost entirely of voids, shaped by forces and energy into the form you call you. In a very literal way, you are a small universe of particles orbiting each other in vast fields of emptiness. Now we have explored the microscopic character of space, the quantum foam and the atomic void. We've seen that even when matter is present, it's built on a framework of emptiness, and even when nothing is present, space is still far from idle or empty. The calm void of night harbors deep activity at tiny scales and comprises the majority of the volume of any solid thing. Space pervades every corner of existence. It is above us in the cosmos and within us in each atom. Let's step back out to the cosmic scale again. We've marveled at gravity and quantum foam and the space within atoms. But what about the shape of the universe as a whole? Does this infinite darkness go on forever? Does it curve back on itself like the surface of a planet? These questions have intrigued humanity for as long as we've looked up and wondered. Is space infinite, or is there some kind of boundary or loop? With modern science, we have attempted to measure the geometry of the universe. The answer isn't fully in, but so far it appears that on the larger scales we can observe, space is extremely flat and likely unbounded. By flat, we mean it follows the rules of Euclidean geometry, the sums of angles in triangles, etc., as far as we can see. If space had a noticeable curvature, we would detect distortions in the patterns of galaxies or the light from the early universe. The results? All measurements indicate that space is extraordinarily flat on the biggest scales. If there is curvature, it is so gentle that our observable universe, a sphere of about 93 billion light-years in diameter, doesn't reveal it. To use an analogy, Earth appears flat to someone walking a few miles because it's so large that the curvature isn't obvious at that scale. Similarly, the universe might be curved in some way, but on the scale we can survey, it looks effectively flat. What does flatness imply for the extent of space? It suggests that space could be infinite, extending forever in all directions, or it could be finite, but without boundary, like how the 2D surface of a sphere is finite area, yet has no edge, except extended to three-dimensional space. If space has positive curvature, like a 3D sphere, it would be finite in volume, and if you traveled far enough in one direction, you might eventually end up where you started, just as an ant crawling on a basketball eventually loops around. If space has negative curvature, like a saddle shape, it would be infinite and spread out with a different geometry. A flat universe, the simplest case, can be infinite and just go on and on. Current data lean toward flatness and therefore possibly infinitude, or a curvature radius so immense that for all intents and purposes it is infinite to us. From what we can tell, there is no edge to space, no wall where space ends. If it is finite and curved back on itself, going in a straight line could, in theory, bring you back to your starting point after an almost inconceivably long journey. We have looked for evidence of light wrapping around the universe, like seeing the same galaxies repeated from opposite directions, which could happen if space were closed and not too large. But we haven't found any such patterns. If the universe is finite and closed, it's far larger than the volume we can see. If it's infinite and open, it just has no end. In either case, there's no boundary that says, beyond here, there is nothing. Space, as far as we know, either goes on forever or loops back on itself. The observable part, what we can see, is certainly finite, but that's only due to the limited age of the universe and the finite speed of light. Beyond that observable horizon, we expect there is more universe, probably much more. We can summarize our findings here. The large-scale universe appears flat and unbounded. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, by satellites and telescopes have narrowed any possible curvature to be extremely slight. So, space is remarkably flat as best we can tell. It might truly be infinite. It might wrap around on a scale so huge we haven't detected it. Either way, for our observable domain, Euclid's geometry holds to a high degree. Parallel light beams do not meet, and the angles of a huge triangle drawn by, say, beams of light spanning billions of light years seem to add up to 180 degrees. This is a clue that the cosmos, on the whole, is not shaped like a sharp sphere or saddle within our view. If it is spherical, the sphere is enormous beyond imagination. If it is saddle-like, the curvature is so subtle that we haven't discerned it yet. In our contemplative journey, lying here under the night sky, it's awe-inspiring to realize we've been able to figure this out at all. By observing distant galaxies and the patterns in the microwave background, humanity has effectively used the universe itself as a giant ruler and protractor. We map the distribution of galaxies and notice that on large scales, they form a sort of cosmic web, filaments of clusters and superclusters surrounding huge, nearly empty voids. Those voids, expanses tens of millions of light-years across with hardly any galaxies, highlight again how dominant space is over matter. Matter forms a delicate lace, and space is the vast expanse between its threads. The cosmic web shows that even on the grandest scale of clusters of galaxies, emptiness stretches out between them, making up the bulk of existence. Indeed, when astronomers survey the cosmos, they see that galaxies are not evenly spread. They line up in filaments and walls, with enormous voids between. Those voids are truly empty regions, aside from perhaps the stray hydrogen atom here or there. Some voids span hundreds of millions of light-years with essentially no galaxies inside. Think about that. Such a volume is mind-bogglingly large, and yet nearly completely devoid of stars, planets, or light. Just tenuous gas and darkness. Those cosmic voids are, in a sense, pure space on the largest scale, a testament to how predominant emptiness is. The luminous matter, galaxies, clusters, outlines like scaffolding on the tapestry of space, but the vast gulfs between that scaffolding are space itself, pristine and quiet. Now, our understanding of space wouldn't be complete without touching on one of the greatest mysteries of the cosmos today, the fact that the universe's expansion is speeding up. We mentioned earlier that the universe is expanding like a rising loaf of bread, carrying raisins, galaxies, apart. You might expect, intuitively, that this expansion would slow down over time. After all, gravity is pulling galaxies toward each other. Indeed, for a long while after the Big Bang, the expansion did slow as gravity reined it in. But to astronomers' astonishment, in the last few billion years, the expansion has begun to accelerate. Galaxies are flying apart faster and faster. There is something in space, some form of energy tied to the vacuum itself, that is pushing the universe outward. We call this strange phenomenon dark energy. The name is just a placeholder, really, a label for our ignorance. It was discovered in the late 1990s when two independent teams observed distant exploding stars, supernovae, and found them dimmer, and thus farther, than expected. It was as if, over the billions of years their light traveled, the space between us and those supernovae had stretched more than it would have in a decelerating universe. At first, this result was met with surprise and a bit of skepticism. Could the expansion be accelerating? That was contrary to everything we thought. Even Einstein, long before, had considered a static, or at most slowing universe. But one by one, other evidence accumulated. Detailed maps of the cosmic microwave background and surveys of galaxy clustering both pointed to the same conclusion. Some kind of repulsive effect is at work on cosmic scales. By the early 2000s, the verdict was clear. The expansion of the universe is speeding up. So what is dark energy? In short, we don't know. It appears to behave like an intrinsic property of space. Like each cubic meter of vacuum has a certain tiny amount of energy that doesn't dilute even as the universe expands. If that's true, then as space expands, you get more vacuum, and thus more of this energy, causing expansion to push even harder, a runaway effect, though fortunately a very gradual runaway. Roughly 2/3 of the universe's total energy content today seems to be this dark energy. Only about 1/3 is in matter, mostly dark matter, plus a few percent normal matter like atoms. That means most of what's out there is this mysterious energy of empty space. It's dark because we can't see it or touch it. It doesn't emit light. And it's energy in the sense that it does work on the universe. It's causing space to swell. We sometimes describe dark energy as a negative pressure or an anti-gravity effect of the vacuum. It's as if emptiness itself has a springiness, a tendency to expand. Every bit of empty space gently pushes outward on itself. The effect is extremely weak on small scales. It's completely overwhelmed by local gravity or even the forces binding galaxies. But on the vast scale where gravity's pull has been growing weaker as galaxies get farther apart, eventually this subtle pressure took over and started accelerating the expansion again. The concept of dark energy reminds us how much we still don't know. It humbles us. We see its effects, yet the cause remains elusive. It could be something fundamental about space that we have yet to understand, perhaps related to that quantum foam energy we talked about. Those straightforward calculations of vacuum energy don't match the observed dark energy. That's a huge puzzle in physics. It could be a new field or fluid pervading the cosmos, or an adjustment needed in our theory of gravity at large scales. We gave it a name, but naming is not understanding. Dark energy is truly a question mark at the heart of cosmology. In essence, what we know is this: empty space isn't just inert nothing. It has this property that is making the universe fly apart faster and faster. The same emptiness between galaxies carries an unknown energy that currently drives the fate of the entire universe. Far from being an irrelevant void, space, through dark energy, will determine how the cosmos evolves trillions of years into the future. To put it succinctly, something latent in empty space, call it dark energy, is accelerating the expansion. The void has a sort of built-in push. This discovery is as dramatic as when we first learned space can bend. It tells us that space has a mind of its own, so to speak, a propensity not only to warp when mass is present, but to grow even where mass is absent. It's as though emptiness has a gentle heartbeat, steadily pumping the universe larger. So now we have seen space from two extreme perspectives: the microscopic, roiling with quantum fluctuations, and the cosmic, swelling with dark energy. We've also seen space permeating matter in atoms. It is clear that space is not a passive backdrop. It's dynamic and rich. Let's recap our journey so far in simpler terms. Gravity taught us that space is flexible. It can bend, fold, and ripple. Relativity taught us that space and time are united. Quantum physics taught us that space is restless at small scales. It's never truly empty. Modern cosmology taught us that space can expand and carries a mysterious energy in its very form. And everyday life and atomic physics taught us that even seemingly solid matter is mostly space inside. Now, with these insights, consider what space really is. It's not empty. It's the very medium of existence. Space is the canvas on which the masterpiece of the night sky is painted, and also the paint and pigments in that masterpiece. It is the medium through which light travels, and also an actor that shapes the story. By bending light, for example, as in gravitational lensing, where space curves around a massive galaxy cluster and bends the light of more distant galaxies into arcs. Space is the connector between distant objects, the silence that allows a conversation via light or gravity to happen across cosmic distances. Space is the stage on which all cosmic drama unfolds, and yet it is also an actor, shaping the plot with its curves and expansions. It is the ocean on which galaxies sail and the gentle tide that carries them apart. Space is a teacher of humility. It shows us that even what seems empty can hold unimaginable power and significance. It reminds us that absence can be potent, that silence can speak volumes. The stillness of space, which once seemed like nothingness, in fact contains the code that dictates the evolution of the entire universe. When we consider the scale of space and how much of everything is made of it, we might feel small, but there is comfort in it too. Space is a comfort in its constancy. It's been here since the beginning and will be here long after the end of all things. When we feel overwhelmed by our day, we can look up and remember how vast and enduring the universe is. Our worries shrink in the face of that perspective, not to trivialize them, but to soothe us with the knowledge that we're part of something much larger and older, where many troubles have come and gone under the eternal sky. Even our ignorance, like the mystery of dark energy, is a kind of tribute to how subtle and profound space is. It's astonishing to realize that only a century ago, we didn't know any of this. We thought the Milky Way was the entire universe, and we believed space was just an empty void that played little role. Now we've learned so much, that the universe is expanding, that space and time bend, that there are countless other galaxies, that space can erupt with virtual particles and drive cosmic acceleration. Each discovery has only deepened the wonder. Knowing that space can ripple and boil and propel galaxies doesn't take away the magic of the night sky. It adds layers of awe to it. The more we comprehend, the more we appreciate how extraordinary it all is. Finally, let's ponder one more speculation that stretches our imagination to the limit. The possibility that our universe's space is not the only space. Could it be that beyond the observable universe, or in dimensions or contexts we cannot see, there are other universes, other expanses of space-time, disconnected from ours? In other words, a multiverse. This idea is highly speculative, yet many scientists consider it plausible given certain interpretations of cosmology and quantum theory. One scenario arises from cosmic inflation, the extremely rapid expansion that likely occurred fractions of a second after the Big Bang. Inflation might not have ended everywhere at once. It could be bubbling continuously, even today, in distant realms beyond our horizon. Each bubble that inflation drops out would become its own universe with possibly different properties. Our universe would be one bubble among potentially countless others in a frothing metacosmos. To visualize this, imagine stepping outside our universe, a mind-bending thought, and looking at a larger sphere of reality. You might see an eternally expanding space like boiling water, with bubbles forming here and there. Each bubble is a universe, perhaps with its own galaxies and laws of physics. Ours is just one bubble that happened to inflate and then slow down, allowing stars and galaxies to form. Some bubbles might remain forever separate, carried away by relentless inflation in between. Others might occasionally collide, potentially leaving subtle imprints. People have even searched our sky for patterns that could be from a collision with another universe bubble, though none has been confirmed. In this view, reality is far grander than what we can see, a multiverse of universes. Another multiverse concept comes from quantum mechanics, the many worlds idea, where every quantum event splits reality into multiple branches. In that interpretation, there is a vast ensemble of parallel outcomes, parallel universes coexisting in a larger quantum reality. If true, There might be another version of you in a parallel world where some decision or event went differently. This is a different flavor of multiverse, more about layers of reality stacking on the same space rather than separate bubbles of space. But it underscores how space might be part of a much larger tapestry. Whether through cosmic inflation or quantum many worlds or other ideas, like perhaps a cyclic universe that periodically resets, the multiverse remains a hypothesis. We have no direct evidence of other universes. We may never have. It is a mind-expanding possibility, essentially suggesting that what we used to call the universe, meaning everything, might be just a tiny piece of an even vaster existence. If it's true, it's the ultimate Copernican revolution. Not only are we not the center of the universe, but our universe might not be the only one of its kind. Just one bubble in an endless foam. Such a concept can be daunting, but it can also be oddly comforting. It would mean creation is endlessly fertile. That reality tries every possibility, that somewhere, everything that can happen does happen. It also could provide an answer to that question of why our universe has the conditions it does, why the constants of nature are fine-tuned for life. If there are countless universes with varying conditions, we naturally find ourselves in one of the rare universes that is compatible with observers like us. In a multiverse, our hospitable cosmos isn't a 1 in a billion fluke so much as an inevitability among infinite tries. We should stress that the multiverse is still speculative. It's an idea, albeit one that arises from serious physics theories, but we have yet to find a way to test or observe it. It remains a tantalizing possibility on the fringes of our understanding. Whether true or not, just contemplating it broadens our perspective even further. It tells us that space, that fundamental thing we've been exploring, might come in an endless variety of forms across different universes. Perhaps some universes have more dimensions of space, or different kinds of particles, or maybe no matter at all, just endless empty space-time, expanding or contracting. The possibilities are endless. Even if the multiverse remains unproven, thinking about it does one certain good. It underscores just how precious our particular universe is. We have this vast cosmos to explore and understand, full of wonders like those we've discussed tonight. We might be essentially alone, with no other universes ever reachable, or we might be one among billions. Either way, our task and our joy is to know our universe as deeply as we can and find our meaning within it. Now, let us gently return to where we began, to the simple stillness of the night and the feeling of space around us. After journeying through curved space-time and quantum foam, across the cosmos and into the atom, we come back to ourselves, lying here under the sky, whether literally or in our mind's eye, quiet, at peace, and maybe a little wiser. The night is still as it was, but we are not the same. The darkness holds more meaning now. We can sense, behind the silence, the faint echoes of all those phenomena we've talked about. The whisper of space-time, the hum of the quantum vacuum, the faint pressure of dark energy, the quiet spaciousness within our very cells. The stillness around us resonates with the knowledge that it is not an empty stillness at all, but full of structure and story. Space is not empty. It's imbued with the fabric of existence. It connects everything to everything else. In this darkness, the light from distant stars travels. The space allows it to move at the fastest speed possible. The gravity of the Earth extends through space to tug on the moon. Fields, like the electromagnetic field, permeate space and allow radio waves, visible light, X-rays, all forms of light to propagate. Invisible geomagnetic fields from Earth reach out into space around you right now. Space truly is the medium in which all things exist, and through which all interactions occur. If it were somehow removed, all those interactions would vanish, and nothing could happen or even be. Consider some of the roles of space we've encountered. Space is the canvas on which galaxies paint their grand designs, and also the weaver that curves and folds itself to create gravity's effect. Space is the nurturer of structure. Its quantum fluctuations seeded galaxies, and its expanses gave them room to grow. Space is the arena of all history. Every event that has ever happened, from the birth of a star to the firing of a neuron in your brain, took place in space-time. Space is the ultimate connector. When you touch a loved one's hand, it's the space and electromagnetic force fields in that space, between the atoms of your hand and theirs, that communicates the pressure and warmth. Space is a teacher. It teaches us that what appears empty can be full, that absence can have presence. It is a guardian of the universe's secrets, hiding dark energy within itself, keeping the ultimate fate of the cosmos in its hands. And space will be the stage for the universe's far future. Looking trillions of years ahead, one can envision a time when space will be virtually all that remains. As the eons pass, galaxies outside our local group will drift farther and farther away, eventually vanishing beyond the horizon, their light stretched into oblivion by the expanding space. The night sky will grow emptier as distant stars disappear from view. Trillions of years from now, even the stars in our own galaxy will exhaust their fuel. One by one, they will wink out, leaving behind faint embers, white dwarfs, neutron stars, and black holes. These remnants will gradually cool and evaporate, in the case of black holes, via Hawking radiation, over an incomprehensible span of time. The universe will continue to expand and cool toward a state of almost complete darkness. In that far future, no new stars are born. No bright galaxies light up the sky. What remains is largely space itself. Vast, cold, nearly empty, studded only sparsely with subatomic particles and the fading whisper of photons from long ago starlight. And yet, through it all, space endures. The same fabric of space-time that was there at the fiery birth of the cosmos will still be there in that silent twilight eons hence. The stage persists even after the actors have left. Perhaps that will be the final chapter of our universe. An ever-expanding dark volume of nearly pure space, quietly extending into eternity. Perhaps, someday, quantum fluctuations within that nothingness might seed a new Big Bang, a new universe, a speculation in some cyclic cosmologies. But either way, the legacy of space is that it is the last cosmic witness. When all else has come and gone, space will still be here, silent and waiting, as it was in the beginning. Space is, in a sense, the alpha and omega of the universe, present at the start, shaping everything in between, and remaining at the end. Now, back to this moment. The night is deep and beautiful. The quiet around you, this gentle void, is the same entity we've been contemplating in all those extraordinary ways. Let that sink in. The empty air and space enfolding you right now carries the heritage of the entire cosmos. It carries the gravity that holds you to Earth. It carries the starlight that reaches your eyes. It carries the potential for future worlds and the echo of the very birth of the universe, a faint whisper of microwave background that bathes all of space, even now, at about 2.7 degrees above absolute zero, giving the night a slight warmth. This space around you is part of the same continuum that bends around a black hole and expands between galaxies and buzzes with vacuum energy. You are deeply connected to the universe through space. You always have been. It's impossible to be truly isolated because the fabric of space links you to the furthest galaxy and the smallest atom. When you look at the stars or simply breathe the night air, that connection only becomes more apparent. You are a child of space, born from stardust that coalesced in space, sustained every second by the oxygen and photons traveling through space. And ultimately, when you return to dust, your particles will drift in space again. Bask in that realization. You belong. You belong here in the universe, and it belongs in you. The boundary between you and out there is not a wall, but a porous membrane constantly exchanging matter and energy. You inhale the atmosphere, drawing in molecules that might once have been exhaled by ancient trees or dinosaurs, and ultimately originated in cosmic processes. You exhale, and your breath's atoms eventually mix into the sky and beyond. In a physical sense, you are never separate from the universe. You are always in communion with it. Take another slow, gentle breath. Feel the cool air fill your lungs, and know that even that simple act is an interaction with space. As the air spreads in your lungs, it's essentially molecules finding room in the internal space of your body, delivering oxygen to your cells across microscopic gaps. As you breathe out, you're releasing carbon dioxide that will travel through the atmosphere, maybe feed plants, maybe one day waft into the upper sky and beyond. Through you, the earth and space are linked. Now, you have permission to let go of all these thoughts if you wish. You don't need to actively think about curvature or quantum foam or dark energy anymore tonight. The knowledge is there, settled gently in the back of your mind, enriching the way you feel the night. You can simply relax in the feeling of it, the feeling of being part of this vast, ongoing cosmos. Above, the stars continue to shine, distant and silent. Around, the darkness remains calm and embracing. You might sense in your own body a mirror of the cosmos, the rise and fall of your chest like the expansion of space, the circulation of blood like galaxies drifting in their clusters, the neural flashes in your brain like tiny starbursts. In the stillness, you can almost feel the subtle humming connection between your life and the wider universe. You are safe. You are weightless and free. The quiet of space enfolds you like a warm blanket. Feel how the whole universe supports you in this moment. The ground beneath you, the air around you, the sky above. You belong here. You are part of all this. There is nothing you need to do right now except be. Just exist. Just rest. Inhale the stillness. Exhale any worry. Let yourself float on the calm of the cosmic ocean. You are safe. You are embraced by existence. You are at peace. No matter where you go, you carry this home of space with you. It was there at the first moment of your life. It sustains you each day, and it will remain long after we are gone. The stillness that surrounds you is the same stillness that cradled the young universe and that will hold the final stars as they wink out. You are truly home in this stillness. It is the cradle of everything. All the understanding we've gained about gravity, time, quantum foam, expansion, and so on, leads to a simple, profound truth. Space is not empty. It is everything. It is the foundation and framework of existence, and you are not separate from it. You are one with it. An expression of the universe, a part of space becomes self-aware. When you gaze at the night, the universe is gazing back at itself through your eyes. So rest now, gently, in the embrace of space. Feel the deep peace of knowing that you are held by the same darkness that carries the stars. The infinite extends around you, quiet and caring. Let go of any remaining tension. Let it fall into the vast well of calm that is space. Let your thoughts drift like gentle clouds across the sky of your mind. No need to chase them. They can float away into the darkness, leaving you calm and clear. You are safe. You are weightless. You are free. The endless silent universe enfolds you, and you belong to it. You are a part of it all, and it is a part of you. In this profound unity, you can release all fears and rest. The night is very quiet now. Around you, the earth sleeps, and the cosmos watches in patient silence. Feel your heartbeat slowing, peaceful. A tiny clock kept by space-time within you. Feel your breaths becoming soft and rhythmic, the same rhythm that pervades all of nature. There is no rush. Time flows at its own gentle pace. Space provides limitless room for your dreams to unfold. You are home in the universe. You are never alone. The space that fills your room, your lungs, and your heart connects you to the furthest galaxy and to the beginning of time. In this knowledge, you can truly rest. All is tranquil. All is as it should be. Stillness. The stars shine. The galaxy slowly turns. The universe breathes in and out on timescales far beyond comprehension. And here, in this quiet moment, you breathe softly, in unison with the cosmos. The stillness of space is within you and around you. Let it lull you into a deep and gentle sleep. Feel yourself drifting, weightless, on a calm, cosmic sea. There is nothing to fear in this dark. It is the same darkness that gave birth to the first dawn. There is everything to love in this silence. It carries the echoes of creation and the promise of eternity. You are safe, you are connected, you are at peace. Sink deeper now into the comforting dark. The universe holds you like a parent cradling a child. The ground beneath you, the sky above, all is one with you. Your mind is quiet, tracing the outlines of these truths with a final, drowsy sense of awe. What remains is not calculation or analysis, but a simple reverence for existence. In the grand sanctuary of space, you close your eyes, your breathing slow and steady. The boundary between yourself and the night dissolves. You are the universe, and the universe is you, a wave returning to the ocean of space. Rest now in that knowledge. Rest in the arms of the cosmos. Feel the profound stillness, the gentle, omnipresent support of space beneath you, holding you up as it has held up worlds and suns and galaxies. Let that stillness fill you. There is nothing more to do, no more striving needed. Just be. Just let yourself go, like a leaf floating on a vast dark pond, carried by the calm currents. Space will watch over you. It has always watched over everything. Your mind is calm. Your body is relaxed. The stars continue their silent vigil overhead, and you drift closer to sleep, carried by the same silence that spans the light years. The feeling of space, that stillness, that openness, that gentle cradle of all things is all around you, and it soaks into your very bones. In this moment, you are that stillness. There is no separation. Quietly, the universe whispers you a lullaby in the language of silence. It says, "You are home. You are home." Let yourself drift in this infinite peace, stillness, silence, space. The journey is complete. The knowledge is within you. The stillness is everything. You are a child of the cosmos, and the cosmos is kind. Feel its love in the quiet of the night. Space is not empty. Space is everything. And you, your atoms, your mind, your life, you are part of that everything. You always have been and always will be. In the great dark between the stars, there is comfort and belonging. In the stillness here, there is the embrace of the infinite. Be at peace, dear traveler of the universe. You are home in the stars and the night. The space around you is your space. The silence around you is your silence. Nothing separates you from the whole. You are safe. You are loved. You are one with the deep, eternal stillness of space. Rest now in that eternal stillness. Let the quiet carry you into restful sleep, as gently as a mother rocks a baby, as naturally as night becomes dawn. The universe holds you. Stillness, silence, sleep. Good night, child of space. The cosmos within and around you watches over you, now and always. Stillness. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, People have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our Sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery, a cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens: ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars, which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc2. 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10^26 watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger, more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue-white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion, so hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our Sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The Sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the Sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the Sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the Sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the Sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The Sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the Sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the Sun's mass, this red giant stage is essentially the beginning of the end. After perhaps 1 billion years in the red giant phase, the Sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the Sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The Sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the Sun's shed gases will mix into the interstellar medium, enriching it with elements the Sun made. All that remains of the Sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our Sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1 million times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star. But once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. A powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant, composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the Sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our Sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly. Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1, half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy, and in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium. And here, the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars. In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly a billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia Sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way, stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution. Myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if star birth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun. Like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1 because its precise radio pulses were so mysterious they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually spiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron-star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron-star collisions forge many of the universe's heaviest elements and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our sun stands alone. Yet the sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension. And yet, the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun, like stars, harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun, like star with an Earth-ish planet, might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story. And just as stars give birth to planets, planets can influence stars in subtle ways. Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point. By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms. And when it does, It will light up our sky brilliantly for weeks. A spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own Sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the Sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the Sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of two white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths, stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns. Look up on a clear night, far from the city lights. Above you stretches an endless dark ocean sprinkled with stars. The longer you gaze, the more stars appear, as if the universe is revealing a secret tapestry. Each star is a sun, distant and powerful. Our own sun is just one among hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is one among trillions. In fact, astronomers estimate there may be 2 trillion galaxies in the observable universe. Try to imagine that. 2 trillion island universes, each brimming with stars beyond counting. If you could snap your fingers and count one galaxy per second, you'd be counting for over 65,000 years just to list them all. Within those galaxies are countless worlds. Some scientists say as many as 6 billion Earth-like planets may orbit stars in our Milky Way alone, and perhaps 12 quintillion across the cosmos. 12 quintillion Earths, 12 quintillion possibilities. The scale of space truly defies comprehension. It's a void, a vastness, but also a canvas of nearly infinite possibilities. Floating on a tiny rock called Earth, We humans have always felt small under this sky, tiny yet special, because we can ponder it. We can ask, what is all this? What is the nature of space, of reality? How amazing that the universe is comprehensible enough that we can study it, yet mysterious enough to inspire wonder. As the famous astronomer Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We are made of atoms forged in long, dead stars, now come alive to gaze back at the sky. Through us, the universe questions its own existence. And one of the most profound questions we can ask is, are we even real? Could all this enormity, this grand cosmos, be an elaborate illusion or construction? Could we, our lives, our planet, our universe, be part of a grand cosmic simulation? That question sounds like science fiction, yet it has leapt from the pages of novels and movie scripts into serious scientific and philosophical debate. What if our reality is not the base reality? What if it's a program, running on some unfathomably complex computer, created by entities beyond our realm of existence? It's an idea that can feel both thrilling and unsettling, the simulation hypothesis. In essence, this hypothesis suggests that what we perceive as the physical universe, including space and time, might be an artificial simulation, like a high-resolution virtual reality designed by an advanced intelligence. In other words, maybe we are living in someone else's computer program. Pause for a moment and really consider that. The ground beneath your feet, the air you're breathing, the light from those distant stars, could all of it be code? If it were true, if everything we know is part of a simulation, how would we know? Would it even matter to us inside it? And who, or what, might be the programmer of the cosmos? These questions take us to the edge of what science can speculate and what philosophy can ponder. They force us to confront the nature of reality from a perspective that is both deeply cosmic and intensely personal. Tonight, we'll embark on a journey through this maze of ideas. We'll wander the vastness of space, marveling at its wonders, and we'll delve into the simulation hypothesis, examining why some prominent thinkers believe it might be true and why others remain skeptical. We'll touch on ancient philosophical puzzles and cutting-edge scientific experiments. We'll meet the scientists and philosophers wrestling with these questions, from those studying the quantum underpinnings of reality to technologists pushing the boundaries of virtual reality, to philosophers questioning whether real and simulated are even meaningful distinctions. Along the way, we'll peer into the very code of the universe and see if there are hints that reality has a designer, and we'll imagine what it would mean for our lives, our purpose, our future, if we are indeed characters inside a grand cosmic simulation. This idea, questioning the reality of reality, is not entirely new. Long before computers and simulations, humans sensed that the world might not be exactly as it appears. Over 2,000 years ago, the Greek philosopher Plato proposed a famous allegory. Imagine people who have lived chained in a dark cave all their lives, Plato said, facing a blank wall. All they ever see are shadows cast on that wall, shadows of objects behind them, objects lit by a fire. Those shadows are their entire reality. They give them names. They think they're real things, but they're just projections, mere silhouettes of something truer. One day, a prisoner is freed and stumbles outside into the dazzling sunlight. For the first time, he sees the full, rich world beyond the cave and realizes the shadows were just a pale imitation of reality. Plato used this allegory of the cave to discuss knowledge and enlightenment, but it resonates eerily with the simulation idea. If we are like those cave prisoners, then our day-to-day world might be the shadow play, while the true reality exists outside our current perception. Could it be that we are living in a cave of sorts, seeing shadows and mistaking them for the whole of existence? Across cultures, similar notions appear. In ancient Chinese philosophy, Zhuangzhou wrote of a vivid dream in which he was a butterfly fluttering about. In the dream, he was happy, unaware of any other life. When he awoke, he found himself lying in bed as a man, but then he wondered, was he a man who had dreamed he was a butterfly, or a butterfly now dreaming he was a man? This butterfly dream story captures a deep puzzle. How can we know if our experience right now is real, or some kind of dream or illusion? Likewise, in Hindu philosophy, the concept of Maya describes the world as an illusion, a sort of cosmic play. And the French philosopher René Descartes, in the 17th century, famously imagined an evil demon that could be tricking him with an illusory world, an early pondering of a virtual reality created to deceive the senses. Descartes realized the only thing he couldn't doubt was his own mind's existence, which is not so far from the simulation question. If everything was simulated, the one thing we might be sure is real is our own consciousness experiencing it. We humans have a long history of questioning reality, but the simulation hypothesis, as we discuss it today, took these age-old questions and reframed them in the context of modern technology and cosmology. It's as if the ancient philosophical doubts met the era of computers and video games and found a new form. A key moment in popular culture was the release of The Matrix in 1999, a film that riveted audiences with its depiction of humans unknowingly trapped in a perfectly simulated world. People plugged into a virtual reality, living in a shared illusion while their bodies lay elsewhere, asleep. The Matrix wasn't the first story of its kind, but it presented the idea so powerfully that it became a cultural touchstone for this concept. Suddenly, the question, what if we're in a simulation, moved from esoteric philosophy to everyday conversations. After watching Neo choose between the red pill and blue pill, a whole generation had a reference point for discussing the nature of reality. Just a few years after that film, in 2003, a philosopher named Nick Bostrom at Oxford University gave the simulation idea a rigorous academic form. Bostrom wrote a paper with a title that cuts straight to the core: Are you living in a computer simulation? In it, he proposed a sort of logical argument, a trilemma. It goes something like this. 1. Almost all civilizations at our stage of technological development go extinct before they ever become technologically posthuman. In other words, maybe it's incredibly rare to survive long enough to create the kind of computing power needed for world-sized simulations. 2. If a civilization does reach that advanced stage, perhaps almost none of them would be interested in running simulations of minds like their ancestors. Maybe it's simply not done, whether for ethical reasons or lack of interest. 3. If the first two propositions are wrong, then the number of simulated conscious beings would far, far exceed the number of original beings. And if that's the case, the odds are that we ourselves are among the simulated minds, not the original biological ones. Bostrom argued that at least one of those three must be true. Either we're doomed to never reach that advanced stage, or we'll reach it, but never simulate worlds with conscious beings, or we're almost certainly in a simulation right now. Importantly, if you think there's any significant chance that advanced civilizations would run such simulations, then you have to admit the possibility that we might be in one. To put it another way, unless we go extinct or never bother to use our future computers this way, it's quite likely that reality as we know it is a digital illusion. That's the unsettling logic Bostrom presented. He even concluded, somewhat playfully yet provocatively, that the belief that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. In simple terms, we can't have it both ways. We can't both expect our descendants to create loads of simulated worlds and also assume we're in the one real world. If creating simulated universes becomes possible and common, then statistically, our own reality is probably one of the many simulations rather than the one original. This argument hit the scholarly world like a jolt. It was a serious professor, not a Hollywood director, suggesting this mind-bending scenario in earnest. And it came at a time when computing power was growing exponentially, and our own simulations, think computer games, virtual reality experiments, AI programs, were becoming more impressive every year. Bostrom's paper gave a sort of credibility to an idea that, until then, was mostly science fiction. It moved the conversation into journals and conferences. People began to debate, not just, could this be true, but what evidence would there be, and how would this change things? It didn't stay in academia. The idea spilled out into tech companies, into late-night dorm room discussions, into Reddit forums and YouTube channels. Even major public figures started taking it seriously. Perhaps the most famous among them is entrepreneur Elon Musk, known for his ventures in electric cars and space travel. Musk has repeatedly talked about the simulation hypothesis. In 2016, speaking at a conference, he put it in his characteristically blunt terms. There's a 1 billion to 1 chance we're living in base reality, meaning he thinks the odds that our reality is the original reality are almost zero. In other words, Elon Musk believes it's extremely likely that we are living in some kind of computer simulation. That statement grabbed headlines around the world. Here was one of the most high-profile innovators on the planet, casually asserting that everything we experience might be artificial. Musk's rationale was simple. Look at the trajectory of video games. In the 1970s, we had Pong, 2 rectangles and a dot. Today, we have hyper-realistic 3D simulations with millions of players in richly rendered worlds, and virtual reality technology that can trick our senses for a time. Given another few decades or centuries, the argument goes, it's inevitable that our technology will produce simulations indistinguishable from reality. If we have that potential, then perhaps some other civilization in the universe already achieved it. And if even one civilization did, the number of simulated universes could be astronomically large. So from Musk's perspective, the math makes it hard to believe we are the one lucky draw that is actually real. He's not alone. Astrophysicist Neil deGrasse Tyson, a science communicator who hosts TV shows and podcasts, has said he thinks there's a very high chance the universe is a simulation. At a debate in 2016, Tyson suggested the likelihood might be better than 50-50 that we live in a simulation. Philosophers like David Chalmers and physicists like Max Tegmark have also entertained the idea in public discussions. Suddenly, the simulation hypothesis has moved from a fringe idea to a topic discussed by scientists at prestigious forums. In fact, the American Museum of Natural History held an entire panel debate on it, with experts from different fields. One journalist described that debate, noting that philosophers, physicists, technologists, and, yes, comedians are all grappling with the idea. It has, in a sense, become mainstream speculative thought. But let's step back a moment. Is there any evidence for this idea, or is it all circumstantial and philosophical? Why would serious people even consider that we might detect the telltale signs of a simulation? To explore that, we need to delve into the nature of physical reality itself, into space, time, and the quantum realm, and see if our universe behaves the way we'd expect a base reality to behave, or if it has quirks more suggestive of a programmed environment. First, consider the nature of space. We usually think of space as simply emptiness. You might picture the void between stars as a silent, cold nothingness. But in physics, space is not truly empty. It has properties. It can bend, ripple, and even boil, with tiny particles popping in and out of existence. According to Einstein's theory of general relativity, space is like a fabric that can stretch and curve. Massive objects like stars and black holes warp this fabric, which is what we feel as gravity. Space, in this view, is dynamic. It's not just an empty stage where things happen, it's part of the actors. When we observed gravitational waves from colliding black holes for the first time in 2015, it was literally space itself trembling, like a pond rippling when a stone is dropped. This is a far cry from the simple nothingness one might assume space to be. Now, zoom down to the tiniest scales, and space gets even weirder. In quantum mechanics, even what we call a vacuum seethes with activity. Particles and antiparticles can spontaneously appear in pairs, exist for a fleeting moment, and annihilate each other. A phenomenon allowed by the quantum rules, as long as it's brief. This isn't science fiction. It's been experimentally observed. If you think about it, this is almost like the universe has a constant background computation running, even when nothing is there. It's as if the simulation never truly idles. There's always some processing happening in the vacuum of space, a constant quantum hum. What about the size of space? The observable universe, the part of the cosmos we can in principle see, extends about 46 billion light-years in every direction from us. We often say 13.8 billion years old, but due to expansion, the radius is larger in light-years, and that's just what's observable. Space could be much larger, potentially infinite. If a simulation were to recreate such a vast space in full detail everywhere, the amount of information would be mind-boggling. Could any computer, even one built by gods or advanced aliens, simulate 2 trillion galaxies worth of stars, planets, and particles? It seems intractable, but if we were inside a simulation, there might be ways to cheat and not simulate everything at once. Think of how video games work. When you're playing a game, the computer or console isn't rendering the entire game world at high resolution all the time. It's only rendering what the player is currently seeing or experiencing. Turn away from a scene, and the game might stop calculating it until you turn back. Some have suggested that a universe simulation might do something similar, only calculate details as needed. This ties into one interpretation of quantum physics that's frequently mentioned in the context of simulations: the idea that observation seems to play a role in how quantum events resolve. There's a famous experiment, the double-slit experiment, where particles are fired at a screen with 2 narrow slits. If you don't observe which slit a particle goes through, the particle acts like a wave of possibilities, going through both slits and creating an interference pattern on a detector screen, as if it interfered with itself. But if you set up a detector to watch the slits, the interference pattern disappears. The particle behaves like a single, well-defined object that went through one slit or the other. Simplifying a lot, the outcome changes depending on whether it's observed. To many, this suggests that reality decides on an outcome only when it has to, when an observation is made. This is a cornerstone of quantum mechanics, often summed up as the observer effect. Now, some physicists will caution that it's not that consciousness causes the change per se, just the interaction with a measuring device. But the philosophical interpretation lingers. Perhaps things aren't determinate until they need to be. If you were designing a simulation, that's actually a smart way to save resources. Don't calculate something until someone tries to look at it. In a way, the universe already behaves like that at the quantum level. It's as if there's a level of reality that's in potential form, a haze of probability, and it becomes concrete only upon interaction. Could that be the sign of a rendering engine at work? As Tyson and his comedian colleague Chuck Nice quipped on Star Talk, maybe that's why we have the speed of light limit in our universe. Perhaps the simulation doesn't allow anything to travel faster than light, because then you could get to another star or galaxy faster than the program could load the details. In their playful exchange, Chuck Nice suggested, maybe that's why we can't travel faster than the speed of light, because if we could, we'd be able to get to another galaxy before they can program it. And Tyson added with a laugh, so the programmer put in that limit. It's a joke, but it perfectly illustrates how a computational constraint could manifest as a law of physics. Our cosmic speed limit might be akin to the draw, distance in a video game, preventing us from moving too fast for the simulation to keep up. Let's think about other hints. Some scientists have looked for signatures of discretization in space, essentially evidence that space is not continuous, but made of tiny pixels or chunks, like a digital grid. If the world is simulated, it might be running on a lattice or grid at the smallest scale. In our current physics, we have the concept of the Planck length, which is far smaller than anything we can directly measure. It's often thought of as a scale at which classical ideas of space break down and quantum gravity might take over. If space were truly pixelated, the Planck length might be the size of the pixels. A few researchers have proposed experiments to detect this. Dr. Zohre Davoudi, a physicist at the University of Maryland, has discussed how, if space-time is discrete, there could be slight changes in how high energy particles travel across cosmological distances. For instance, we might detect a tiny preferred direction or an upper limit in the energy of cosmic rays because of the underlying grid. Imagine if you tried to draw a perfectly straight, extremely long line on a pixelated screen. At some point, the discreteness might show anomalies. Davoudi specifically noted that if space-time is on a lattice for the simulation's sake, extremely energetic particles might not behave exactly as expected in a smooth continuum, possibly revealing a break in a symmetry-like rotation. So far, no such anisotropy in cosmic rays has been observed. If one were, it would be intriguing, though not absolute proof of a simulation. But the fact that physicists are even contemplating such tests shows how seriously the idea is being taken. Another striking piece of maybe evidence came from James Gates, a theoretical physicist known for his work in supersymmetry. Gates found something unexpected in the equations he was studying. Deep in the mathematical framework of certain supersymmetric models, he discovered equations that are identical to those used in computer error correcting codes. Error-correcting codes are algorithms programmers use to ensure data isn't corrupted. Basically, they help systems self-correct mistakes. They are, as Gates put it, what make browsers work, allowing digital information to transmit reliably. So, it was quite startling to find them knitted into the fundamental equations describing how particles and forces might work. Gates said, "I no longer can say that people like Max Tegmark are crazy." Upon realizing this, implying that seeing something so digital, looking in the bedrock of physical law gave him pause. He mused that finding such code in nature's equations, if nature weren't a simulation, would be an extremely unlikely coincidence. Does that mean the universe is a computer program? Not necessarily. It could be that our mathematics just happens to take that form, or perhaps there's a deeper reason for those codes that has nothing to do with actual computing. But it's tantalizing details like this that make scientists raise an eyebrow. It's as if you were walking through a forest and found a computer chip lying on the ground. You'd wonder, is there an intelligence at play here, or is it just an odd-shaped rock that happens to look like a chip? Cosmologist Max Tegmark, whom Gates referenced, has pushed an even broader idea, that the universe fundamentally is mathematical. Tegmark often points out that the more we study nature, whether it's the motion of planets or the behavior of subatomic particles, we find that mathematics describes it with uncanny precision. The laws of physics can be written in equations. They have symmetry and structure, much like a code. Tegmark's perspective is that perhaps the universe isn't just described by math, it is math in a very real sense. If one were a character in a video game, he notes, at some point you might notice the strict mathematical rules of your world and suspect there's an underlying code. Our scientists, by uncovering equations, might just be reading bits of the cosmic source code. This doesn't prove a programmer in the usual sense. Tegmark is careful to frame it as the universe being a mathematical structure on its own, but it certainly rhymes with the simulation narrative. After all, what is code if not mathematics implemented in a machine? So from the quantum behavior suggesting on-demand rendering, to potential spatial pixels at Planck scales, to literal error correcting codes popping up in theoretical physics, the universe has some hints that tickle the mind. None of these are smoking guns. For every intriguing clue, skeptics can offer alternative explanations, but they add up to a picture of a universe that is surprisingly information-like. The physicist John Wheeler once coined the phrase "it from bit," meaning that at a fundamental level, everything may arise from binary choices, from information bits. More and more, our best theories of physics speak in terms of information. Black holes, for example, are often described by how they store information on their event horizons. Quantum entanglement is being investigated as the possible pixel glue of space-time itself in some modern theories. Scientists are exploring the idea that space-time geometry might emerge from patterns of entanglement, essentially from information networks. It's almost as if the universe behaves like a giant information processor. And if so, one can't help but ask, who or what is processing that information? Is it just the universe being the universe? Or is it a computer built by something beyond it? Now, let's take a step further out and look at a completely different line of thinking, the Fermi paradox and the eerie silence of the cosmos. In our opening, we talked about the vastness of space and the countless planets that likely exist. Given those numbers, many scientists believe that life, and eventually intelligent life, should have arisen in many places across the cosmos. Even if a fraction of those 12 quintillion Earth-like planets developed life, and a fraction of those developed intelligent civilizations, there ought to be many alien civilizations out there, some perhaps far older and more advanced than us. This reasoning is encapsulated in the Drake equation, which is a probabilistic formula to estimate the number of communicative civilizations in our galaxy. Depending on what numbers you plug in, you might predict anything from 0 to thousands of civilizations, but many reasonable estimates suggest the galaxy should be home to several at least, and the universe at large, many more. So physicist Enrico Fermi famously asked, "Where is everybody? If life is common, why haven't we seen any evidence? No confirmed signals, no spacecraft, no alien visitations that withstand scientific scrutiny. The skies are quiet and have been for as long as we've been listening." This puzzlement is what we call the Fermi paradox. Over the years, people have suggested numerous possible solutions. Maybe life is rare, or intelligent life destroys itself quickly, or maybe alien civilizations are out there but choose to hide or observe us from afar. One particularly mind-bending proposal is directly relevant to our topic. Perhaps we don't see aliens because the universe has been designed to appear empty to us. This is sometimes called the planetarium hypothesis. Imagine we are inside a giant virtual planetarium or terrarium, crafted to give us an illusion that we are alone. In 2001, science fiction author Stephen Baxter wrote an essay suggesting exactly this, that maybe advanced extraterrestrials, perhaps ones who reached a Type 3 civilization on the Kardashev scale, have created a simulation around us so that we perceive a vast, empty universe. They keep us in the cosmic equivalent of a snow globe. We look out and see stars and galaxies, but maybe the details beyond a certain point are all a projected illusion. Baxter wrote that our universe could be a form of virtual reality planetarium designed to give us the illusion that the universe is empty. In this scenario, the reason for the simulation is key. It might be to quarantine us or protect us. Perhaps they worry that if we knew about them, or if we encountered them, it would disrupt our natural development, or cause us to panic. Or maybe it's to protect themselves, ensuring we can't locate them. It's a wild idea, but it does answer Fermi's question in a creative way. We haven't seen aliens because our reality is constructed so that we won't. Whenever we point our telescopes out and listen for signals, the simulation dutifully returns a result of grand silence because that's its programming. If true, it implies our simulators are not necessarily our descendants, but could be alien beings in a higher level reality. They might be running a simulation of the universe and intentionally omitting themselves. It's like we're NPCs in a video game who aren't allowed to meet the game masters. Of course, if that's the case, What happens if one day we humans start reaching out into space in earnest? Baxter mused that maybe the simulation has built in limits to stop us. For example, the laws of physics that limit space travel could be intentional. The enormous cosmic distances and the finite speed of light act as barriers to keep us from ever leaving our sandbox region of the simulation. If somehow we got close to escaping, say we built ships that approach light speed, perhaps the simulators would intervene with some new obstacle. It's a bit like the Truman Show, where the main character tries to sail away from the island and literally bumps into the sky, which is a painted dome. Is our sky, our space, a painted dome in some sense? Hard to believe, and currently impossible to know. But it certainly fires the imagination. Now, before we get carried away, it's important to note that while some researchers find such ideas intriguing, they also acknowledge limitations and criticisms. For instance, can a simulation even be that large and perfect? One challenge is what we call computational complexity. If you were to simulate an entire universe down to the level of atoms or quarks, the amount of computing power seems unfathomable. We struggle to simulate even a tiny chunk of the physical world with our best supercomputers. Simulating the quantum behavior of a few dozen particles can tax our largest machines. In fact, researchers using quantum Monte Carlo simulations find that the complexity grows exponentially with the number of particles. They've pointed out that to simulate just a small piece of reality at full quantum detail might be effectively impossible for any practical computer, even one the size of a planet or a star. So skeptics argue, how could a simulator handle 10 power 80 particles, each doing their quantum dance? Well, proponents of the simulation idea respond that a simulator could use shortcuts. We already touched on one. Only simulate what's needed. Perhaps the simulating computer doesn't bother to calculate the interior of distant stars or the exact behavior of every galaxy unless it becomes relevant to the story. Perhaps it focuses on Earth and its vicinity, and everything else is painted in broad strokes, with detail filling in only when we look closely. Some have even speculated that things like quantum indeterminacy or chaos theory could be features that prevent us from ever predicting and thus compressing the universe's behavior. If the simulators are clever, they might not need infinite power, just very sophisticated algorithms that always stay a step ahead of the players. Another counterargument is Occam's razor. This is the idea that, all else being equal, the simplest explanation that fits the data is preferred. The simulation hypothesis is, to put it mildly, not the simplest explanation. It posits an entire additional layer of reality, with beings and technologies far beyond our own, all to explain a universe that we could otherwise just take as is. Physicist David Kipping performed a Bayesian analysis and initially found about a 50% odds for us being in a simulation, given no prior information. And he noted that, if humanity ever creates simulations of conscious beings, those odds would dramatically tip toward the simulation scenario. But Kipping himself has said that because the simulation idea is so elaborate, Occam's razor might count against it. Without evidence, why assume a complicated multi-layer reality when a single-layer reality works fine? He and others have likened it to a philosophical speculation that may not be testable, and if it's not testable, can it be considered scientific? After all, any evidence we find could be just features of the universe, not proof of external programming. The ultimate problem is falsifiability. We can't currently devise an experiment that would definitively tell us, yes, this is a simulation, or no, it's not. If the simulation is perfect, any result is just part of the simulation. As philosopher David Chalmers put it, there's certainly not going to be conclusive experimental proof that we're not in a simulation. Any evidence we could ever get would be simulated. In other words, a clever simulator could always tweak things to keep us guessing. So some argue, what's the point of even debating it if we can't prove or disprove it? Perhaps, they say, we should just proceed as though the universe is real. Lisa Randall, a prominent physicist, has expressed that she finds the simulation hypothesis pretty implausible and not very useful. We might as well keep doing science and not worry about being in a simulation. She remarked, "We don't know the answer, and we just keep doing science until it fails." If at some point our scientific understanding truly hits a wall that can only be explained by "we're in a sim," then maybe we'll reconsider. But until then, the hypothesis is more of a fun thought experiment than a practical guide. Randall also noted that thinking about such scenarios can still be valuable if it motivates us to ask interesting questions about physics we can test. In a sense, even if we don't buy the simulation theory wholesale, exploring it might spark new ideas or new ways to look at the cosmos, and that is certainly worthwhile. Now, let's imagine for a moment, what if we did discover evidence we're in a simulation? Or suppose one day an anomaly happens that simply can't be brushed aside. Maybe a message appears in the sky that can't possibly be natural, or we find an actual glitch in physics that is so specific it points to design. How would we react? Would it change how we live our lives? There are many science fiction scenarios about this. One could imagine society reacting with denial, or with a religious fervor, or maybe with panic, or conversely with relief. That explains everything. It's hard to know. Some thinkers have said it shouldn't change much on a day-to-day level. If you find out the universe is a simulation, the tree in your backyard is still a tree. The love you have for your family is still real to you. The taste of your favorite food is the same. You still have to go to work, avoid stepping in front of buses and all that. In fact, in a perfectly run simulation, you can't actually do anything outside the rules of the simulation, so you'd have to continue living by its laws. But psychologically, it could be a heavy realization. Would people feel less guilty about doing wrong, thinking, none of this is real, so what does it matter? Or would they feel more purpose, like, we're part of a planned creation, we better make our creators proud? Different individuals might react differently. Interestingly, the simulation hypothesis has a way of merging with traditional ideas of spirituality and religion. If there are creators outside our reality who made our world, how is that so different from concepts of God or gods? Some have pointed out that the simulation argument is like a technologically updated creation story. Instead of a supernatural deity, you have a super intelligent programmer. Instead of mystic heaven, you have another universe that hosts the computer. It reframes phenomena like an afterlife. As Dr. James Gates noted in that panel, if we are in a simulation, reincarnation might be literally possible. Our lives could be restarted or the program run again, effectively bringing everyone back to life. If you've ever played a video game, you know that dead characters can often respawn, or a saved game can be loaded to replay a scenario. In a simulation, maybe death isn't permanent. The data of your mind could be saved or copied. The simulation could also allow for things that look like miracles. Perhaps the simulators can intervene or tweak things now and then, which might appear to us as divine acts or anomalies. It's a whimsical parallel, but it does start to blur the line between science fiction and theology. In fact, Gates said that the simulation idea starts to break down a funny barrier between what people often think is the conflict between science and faith. Because here we have a scenario with creators, possibly an intention or purpose, and potentially even a form of life after death. Yet it's framed in a logically and technologically grounded way, rather than a mystical one. It's almost like a bridge between two worldviews. Of course, not everyone would agree with venerating simulator beings as gods. Philosopher Chalmers quipped that even if we were in a simulation controlled by higher beings, he'd refuse to worship the simulators. After all, they might be just scientists or gamers, not morally superior divinities. And if they allowed suffering in the simulation, one might question their ethics just as we question why a benevolent God would allow evil. Are we just an experiment? Entertainment? Education? Who knows what their motive would be? There's even a theory that maybe it's us, our future descendants, running ancestor simulations to study their own history, which raises all sorts of paradoxes and moral questions about creating conscious beings for study. Bostrom himself pondered on whether it would be ethical to run simulations of suffering. Let's entertain a positive angle. If we are in a simulation, maybe the simulators are benevolent. Perhaps we're a kind of long-term art project, being carefully tended. If at some point we're in danger, maybe they'd subtly steer things to save the project. Some people have humorously suggested that the lack of catastrophic asteroid impacts in recent times, or the fortuitous timing of certain events in humanity's past, could indicate someone wants us to reach a certain stage. That's highly speculative and arguably just human-centric storytelling. But it's true that the simulation idea can either make you feel extremely small or strangely important. Another fascinating speculation: what if we ourselves create simulations within this universe? If we build our own simulated realities, populated by AI beings who think they're alive, then we'd have a nested simulation. Perhaps that's already happened. Maybe the simulators who built our world are themselves simulated by a higher level, and so on. This could lead to a chain of simulations within simulations. Tegmark pointed out a philosophical issue with Bostrom's argument. What stops an infinite regress of simulated worlds? If simulations become common, there could be many layers. But could it be simulations all the way down? At some point, there might need to be a base reality where the first simulation runs. If we're deep in a stack of simulations, our chances of reaching or understanding the true base reality are extremely slim. It would be like a character in a video game becoming aware of the game and then trying to figure out the world of the game developers by only exploring inside the game. They might get some hints, but can't break out of their level. Some tech visionaries have even talked about trying to break out of the simulation. There were reports that certain billionaires in Silicon Valley were funding research to find a way to detect or escape the simulation. It sounds like the plot of a movie. The rich and brilliant trying to crack open the sky of the Truman Show. While those specific stories might be exaggerated, it's true that the simulation hypothesis has captivated some of the most future-oriented minds. If you truly believed we're in a simulation, one radical idea would be to attempt to communicate with the creators. Maybe not by building a physical Tower of Babel, but perhaps by sending a clever message or creating a scenario within the simulation that stands out. Some have facetiously suggested that we should perform bold, unpredictable actions so as to get the simulator's attention. Max Tegmark, at the end of that debate, half-jokingly advised, "If you're not sure whether you're actually simulated or not, my advice to you is to go out there and live really interesting lives and do unexpected things so the simulators don't get bored and shut you down." That might be the best advice regardless of simulation status. Live an interesting, meaningful life, just in case someone is watching from above, and for your own sake if no one is. Now, we've journeyed through a lot, from the starry expanse of space to the subatomic quirks of quantum physics, from ancient philosophy to cutting-edge computational theory, from the loneliness of the cosmos to the possibility that we're not alone at all, but rather surrounded by an invisible infrastructure of a simulation. Through it all, one thing is clear: the line between reality and illusion is delicate. Whether or not we live in a simulation, pondering it forces us to appreciate reality's richness. If our universe is a simulation, it's a masterpiece of one. Think about it. The simulators would have created every coral reef, every nebula, every laugh, every tear, the taste of chocolate, the laws of gravity, the music of Mozart, the equations of Newton, the light of 1,000,000,000,000,000 stars, and they gave us the tools, like science, to start to figure it out. That's quite something. And if this is not a simulation, if this is the one true reality, then it's even more incredible. It means from empty darkness and mindless matter, the universe evolved to a state where it can dance and think and wonder through us. We, tiny specks on a pale blue dot, can question the very fabric of existence. In the end, the simulation hypothesis is a mirror. Look into it, and it reflects our deepest inquiries. It asks how far our intelligence can go, how we distinguish truth, how we find meaning. It has us grapple with what-ifs that challenge our perception of time, space, and ourselves. Are we a cosmic accident, alone in an unconscious universe? Or are we characters in a cosmic play with hidden audience and playwright? Perhaps we'll never know for sure. Perhaps one morning, like Zhuangzi, we'll wake up and realize this was all a dream. Or maybe we'll venture out into space, among the real stars or the simulated ones, and gradually peel back the layers of reality. Until then, the best we can do is live fully and curiously. Simulated or not, this life is the one we have. If it's a simulation, maybe we honor it by being the most interesting simulation we can be. If it's base reality, we cherish the fact that we're part of something truly fundamental. In both cases, our experiences, our joys and sorrows, our aspirations, they matter to us and to those around us. As far as we're concerned, they are real. The philosopher Chalmers might remind us, even if all is a simulation, the simulation is our reality, so it's real to us. So when you next step outside on a crisp night and look up, consider the stars again. Each one could be a distant sun in a vast, real galaxy, or a pixel lit up on the canvas of a sky created for our benefit. Either way, let that sight fill you with wonder. The universe, be it natural or programmed, is majestic and mysterious. We find ourselves alive in the midst of it, able to ask grand questions. That is a privilege beyond measure. In a way, through our eyes, the universe gets to witness something too. A species growing from curiosity, reaching out for truth, striving to understand the infinite. Perhaps that's the point of it all, to wonder. Perhaps the ultimate cosmic experiment is to see if intelligent life can figure out its own reality, or at least learn to live harmoniously within it. We may not have the final answers, but we will keep searching, observing, hypothesizing. We will keep exploring space, both outer and inner, physical and virtual. And as we do, we carry in our minds the profound possibility that reality might be far more layered than it seems. It's a possibility that humbles us, but also elevates our imagination. Real or simulated, the stars still shine down, the night sky still calls to us. The mystery remains as deep and dark as space itself. And in that mystery lies beauty, because a universe without secrets, simulated or not, would be far less interesting. So let's embrace the mystery. Let's cherish the awe we feel when confronted with the cosmos. If we are in a simulation, then let's be the best characters we can be. And if we're not, let's be the best beings this universe can produce. In the end, perhaps it doesn't matter whether our reality is base level or virtual. What matters is what we do with the reality we have. As the great adventure of knowledge and existence continues, we remain, as always, explorers. Explorers of space, explorers of ideas. We stand on the shore of the cosmic ocean, with the waves of the unknown gently lapping at our feet. Above us, the sky, real sky or manufactured dome, is full of stars. We feel small, yet connected to something vast. We feel the urge to reach out, to understand. And so we journey on, minds wide open, hearts alight with wonder. Who knows what we'll discover, what truths or illusions await? The nature of space and the mystery of the simulation hypothesis together form a story still unfolding. Stay curious, keep looking up, and remember, the universe is far more wondrous than any fiction ever conceived. Possibly because, in some way, it might be a fiction, crafted with care. Or perhaps because a simple truth underlies it all. Either way, it invites our curiosity, and that, in itself, is the grandest invitation we could ask for. Now that our main story is to a close, let's list some space facts. Imagine a place in the universe where a single spoonful of material weighs more than Mount Everest. Neutron stars, the ultra-dense remnants of massive stars, are so compressed that just 1 cubic inch of their matter would tip the scales at billions of tons. These stellar corpses are the densest objects known outside of black holes. Their magnetic fields are trillions of times stronger than Earth's, a city-sized ball of neutrons, spinning at hundreds of revolutions per second, crackling with radiation, isolated in the cold silence of space, a lighthouse of doom beaming through the dark. Step outside the airlock of the International Space Station, and something surprising happens. When astronauts return from their spacewalks, they often report a distinct smell clinging to their suits. Not the void itself, but the aftermath of exposure. The odor, burnt steak, welding fumes, a metallic tang. This is the scent of space, or at least how our senses interpret the byproducts of atomic oxygen interacting with spacecraft surfaces. It's the smell of the universe in motion, of particles colliding, of stars being born and dying. Venus, Earth's twisted twin, takes its time. If you were to stand on its blistering surface, where temperatures melt lead and clouds rain acid, you'd notice something even more bizarre than the heat. A single day on Venus, one full rotation on its axis, takes longer than an entire trip around the Sun. That means its day is longer than its year. A planet where the sun rises in the west and sets in the east, crawling through a sky it barely crosses. Time stretches strangely on Venus, and so does our understanding of what makes a planet normal. Far beyond our galaxy, past swirling nebulae and clusters of galaxies, lies something extraordinary. Around a quasar, 12 billion light-years away, astronomers discovered a cloud of water vapor large enough to fill Earth's oceans. 140 trillion times. This ancient fog surrounds a supermassive black hole, glowing brightly with the energy of an entire galaxy. It's the largest and most distant water reservoir ever found. A cosmic oasis in the void, proof that even in the deep past, water flowed freely across the stars. The moon has always been our closest companion, our silent sentinel in the sky, but it's slowly drifting away. Every year, the moon moves about 1.5 inches farther from Earth. It may not sound like much, but over millions of years, it adds up. In the distant future, the moon will be too far to perfectly eclipse the sun. Total solar eclipses, those magical moments when day becomes night, will cease to exist. A celestial goodbye that spans eons, unnoticed in a single human lifetime, but profound in the timescale of the cosmos. Not all planets are tied to stars. Some wander alone. These are rogue planets, dark, cold worlds without a sun, flung into the abyss by gravitational chaos. Billions of them roam the galaxy like cosmic orphans, drifting endlessly through space. With no light to define their days, and no warmth to shape their climates, they remain mysterious. Some may harbor subsurface oceans, heated from within. Others may be completely frozen, locked in a stasis that has lasted since the dawn of time. They are reminders that not every world belongs to a system. Some just float in solitude. The sun, though just one star among billions, is a giant in our own neighborhood. It holds 99.86% of all the mass in the solar system. That means everything else, every planet, every moon, every comet and asteroid, is just debris in comparison. Even mighty Jupiter, the king of the planets, is barely a drop in the solar ocean. The sun dominates not just through heat and light, but by sheer gravitational force. It commands the dance of planets, holds the icy edges of the Kuiper Belt in place, and bends the very fabric of space and time around it. Speaking of time, it's not as steady as it feels. In places of intense gravity, like near a black hole or even on a planet like Jupiter, time flows more slowly. This is not science fiction. It's the bizarre truth of Einstein's general relativity. Gravity warps space-time. The closer you are to a massive object, the slower time passes for you. Live your life orbiting a black hole, and you might experience minutes while years pass outside. Time is elastic in the universe, flexible, strange, and deeply tied to gravity. High above Earth, satellites orbit in perfect balance. But there's something else out there too: space junk. The modern sky is littered with remnants of human ambition, dead satellites, rocket parts, tiny fragments of old missions. Over 170 million pieces of debris now race around our planet, many traveling at speeds faster than a bullet. A single screw could punch through a spacecraft like shrapnel. It's a growing cloud of chaos, and one that we'll have to reckon with if we hope to keep exploring the stars. On the outskirts of the solar system, beyond Neptune, lies a vast and icy graveyard known as the Oort cloud. It's never been directly seen, but we know it's there. A shell of frozen objects encasing the solar system like a bubble. Some comets we see in the sky begin their journey here, drifting for millions of years before the sun's gravity gently tugs them inward. The Oort cloud may stretch halfway to the next star, holding the leftovers of solar system formation, ancient time capsules frozen in deep space. Jupiter is more than just the largest planet in our solar system. It's a shield, a protector, a cosmic vacuum cleaner. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, life here might never have had a chance. But this gas giant has secrets of its own. Beneath its swirling clouds lies a core of metallic hydrogen, a state of matter so exotic it can only exist under immense pressure. Lightning storms larger than Earth rage across its surface, and its iconic Great Red Spot is a hurricane that's been raging for centuries. Saturn's rings are perhaps the most visually stunning feature in the solar system, but they're young, maybe only 100 million years old, and they're vanishing. Slowly, inexorably, the rings are falling into Saturn, pulled down by gravity and magnetic forces. What once dazzled stargazers may one day disappear entirely. The rings are made mostly of ice, ranging in size from dust grains to bus-sized chunks. They're delicate, temporary, a reminder that even beauty on a planetary scale can be fleeting. And then there's Pluto. Once a planet, then demoted, yet still beloved. This distant world has a heart-shaped glacier on its surface and mountains made of water ice. But what's more fascinating is what lies beneath. Scientists believe Pluto may have a subsurface ocean, liquid water under layers of rock and ice. In the frozen reaches of the Kuiper Belt, warmth can still exist, not from sunlight, but from radioactive decay deep within. Even in the coldest places, the potential for life may remain. Let's drift even farther, to a galaxy not so different from our own, one of many. The observable universe contains more than 200 billion galaxies, and each of those galaxies contains hundreds of billions of stars. That means there are more stars in the universe than grains of sand on every beach on Earth. Yet despite this overwhelming abundance, the night sky feels quiet, peaceful, but it is anything but empty. It is alive with movement, with birth and death, with explosions and silence, with radiation and dust. Black holes, cosmic monsters that devour light itself, sit at the heart of many galaxies, including our own. The one at the center of the Milky Way, Sagittarius A, is 4 million times the mass of our Sun. Yet we can't see it directly. It lurks behind a veil of dust and gas, invisible and quiet, unless something dares come too close. Then, space-time tears. Matter stretches into glowing streams as it spirals inward, lost forever. Time itself slows to a crawl. And then, nothing. Beyond the event horizon, not even information escapes. And finally, we return to Earth, our pale blue dot. Floating in a sunbeam, Carl Sagan once said. All the wars, the triumphs, the laughter, and the sorrow, every human story that has ever existed, happened here. Earth is the only known planet to harbor life, but that may not last forever. Our star will die, our oceans will boil, but for now, we are here, thinking, dreaming, wondering, reaching out into the dark. There is a place where stars go to die, a graveyard not of bones, but of white-hot embers. White dwarfs are the final act of small to medium stars like our sun. After billions of years of burning, they shed their outer layers and collapse inward, becoming a sphere of dense, glowing ash. These stellar corpses are no larger than Earth, but can weigh as much as the sun. Over trillions of years, they cool and fade, becoming black dwarfs, cold, dark remnants that may be the final objects left in the universe, long after the last galaxies blink out. But not all stars fade quietly. The largest live fast and die violently. Supernovae are among the most powerful events in the universe, stellar explosions that outshine entire galaxies for brief moments. In that flash, elements like gold, silver, and uranium are forged. Every heavy atom in your body, in the earth, in your phone, was born in a star's fiery death. We are, quite literally, made of star stuff. And those supernova remnants, they seed the galaxy with the building blocks of new worlds. In the vacuum of deep space, silence reigns. Not because there's nothing happening, but because sound cannot travel. Space is not just quiet, it is mute. There is no air to carry sound waves. Explosions, collisions, solar flares, all of it happens in absolute silence. If you were floating next to a star going supernova, you'd see light brighter than anything imaginable, and hear nothing. In space, even the loudest scream is swallowed by the void. Yet even the void is not truly empty. Between the stars, in the vast gulfs of interstellar space, is dust, gas, particles and radiation, invisible forces drifting in the darkness. Entire clouds of molecular gas stretch across light years, slowly collapsing under gravity to birth new stars. These are stellar nurseries, glowing, majestic regions like the Orion Nebula, where stars and planets begin their long journey into existence. The vacuum is pregnant with potential. There are planets out there stranger than anything we've dreamed of. Take HD 1T9733b, a gas giant where it rains glass sideways in 5,000 mile-per-hour winds, or 55 Cancri e, a planet likely made of diamond, its carbon-rich structure compressed by immense pressure, or Gliese 581c, a world that may lie just within its star's habitable zone, with the potential for liquid water. Some planets orbit two suns, like scenes from a sci-fi movie. Others are scorched, tidally locked hellscapes, where one side is a molten desert and the other an endless frozen night. Our universe is expanding, not just objects moving through space, but space itself stretching. Galaxies aren't traveling through a void like ships through an ocean. The ocean is growing beneath them. This discovery, first observed in the redshift of distant galaxies, means that the universe once had a beginning, a single moment of rapid expansion, the Big Bang. And that expansion continues today, accelerating due to a force we still don't fully understand. Dark energy, a mysterious pressure pushing everything apart. Then there's dark matter. We cannot see it. We cannot touch it. But it's there. Its gravity holds galaxies together, keeps clusters from flying apart. It makes up over a quarter of the universe, yet we don't know what it's made of. It neither emits nor absorbs light. It passes through us every second. Like a ghost overlaying reality, shaping the structure of everything we see. Time, too, is not as it seems. In the early universe, the rules were different. Moments after the Big Bang, time and space were chaotic. Energy and matter in a soup of particles and raw forces. The four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once one, unified. Since then, they've separated, cooled, and structured the cosmos. But deep inside particle accelerators, we try to reverse that clock, to glimpse the unity, the primal heartbeat of the cosmos. And yet, with all this knowledge, mystery reigns. We've mapped only a small fraction of the stars. We've only just begun to catalogue exoplanets. We've never been farther than the moon. The observable universe is vast. But beyond it? We don't know. There may be more, far more. Infinite realms, parallel universes, entire other realities with different laws of physics, born from the same cosmic fire as ours. And in all of it, here we are. A species that can ponder the beginning of time, that can send robots to Mars and probes beyond the edge of the solar system, that can build telescopes so precise they can see light from galaxies 13 billion years old, light that left when the universe was still in its infancy. We are the universe, becoming aware of itself. Somewhere far from any star, in the deep interstellar dark, a spacecraft drifts in silence. It's called Voyager 1. Launched in 1977, now over 14 billion miles from Earth. It carries with it a golden record, a time capsule of humanity, music, greetings in dozens of languages, sounds of life on Earth, a whisper to the stars. Voyager 1 has left the solar system. It is now in interstellar space, the first object made by humans to ever do so. It continues its journey, untouched, undisturbed, on a trajectory that may outlast our species. For billions of years, it will drift in the quiet, a ghost of Earth sailing through the endless night. On Earth, the sky looks still, but look closer, and you'll find it's alive with motion. The stars are moving. The constellations we know are temporary, fleeting sculptures shaped by our position in time. In 50,000 years, Orion will look completely different. In 1,000,000 years, today's night sky will be unrecognizable. The stars we navigate by are travelers themselves, orbiting the galactic center, pulling against gravity, drifting through a galaxy that spins like a pinwheel of fire. The Milky Way, our home galaxy, is vast, over 100,000 light-years across. But it isn't alone. We're on a collision course with the Andromeda Galaxy, a spiral galaxy twice our size. In about 4 billion years, the two will merge, tearing and reshaping each other in a gravitational ballet. Stars won't crash. Space is too empty, but their orbits will change. New stars will be born. The night sky will erupt with arcs of starlight, and eventually a new galaxy will form, elliptical, larger, older, a silent monument to cosmic rebirth. Not all galaxies are peaceful swirls. Some are active, chaotic, burning from the inside. At their hearts are supermassive black holes devouring matter so violently that jets of energy blast out across millions of light years. These are quasars, the brightest objects in the universe. They shine with the light of 1 trillion suns. Yet they're powered by darkness, by gravity crushing light itself. When we see a quasar, we are looking back in time to the young universe when galaxies were still growing, still colliding, still becoming. The universe is not cold because it lacks energy. It is cold because it is old. As it expands, the energy of the Big Bang spreads thinner. Today, space itself holds a background temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation. It fills all of space, a faint radio hum from the beginning of time. When you see static on an old television screen, a tiny fraction of that fuzz is the leftover light from the birth of the universe. Gravity is not just a force. It's the bending of space and time. Massive objects, planets, stars, black holes, distort the fabric of reality around them. Einstein showed us that light can curve, that time can slow, that space is not a stage, but a participant. And this bending of reality isn't just theory. We've seen it. When a massive galaxy sits between us and something farther away, it can act like a lens, bending and magnifying the distant light. We call this gravitational lensing. It lets us see galaxies so far away they'd otherwise be invisible. It's as if the universe is helping us see itself. And yet, for all our knowledge, we've only just begun to grasp the full picture. The vast majority of the cosmos is made of things we can't see or explain. Ordinary matter, everything we've ever touched or measured, makes up less than 5% of the universe. The rest is dark matter and dark energy. Invisible. Mysterious. We don't know what it is. We don't know where it came from. But it controls the structure and fate of everything. It's the shadow behind the stars, the silence beneath the light. Every now and then, Earth is reminded of its fragility. An asteroid streaks across the sky, burning bright as it tears through the atmosphere. Most disintegrate harmlessly. Some leave craters, scars from impacts long past. 65 million years ago, such an impact changed everything. It ended the age of dinosaurs. It cleared the way for mammals, for us. We are here because a rock fell from the sky at the right, or wrong, time. And there are still many more out there, orbiting quietly, watching, waiting. But space isn't just death and distance, it's potential. On moons like Europa and Enceladus, icy shells hide oceans below, heated by tidal forces. These alien seas may be teeming with microbial life. We've seen plumes of water erupt into space, carrying hints of organic molecules. If life can thrive there, in darkness, under pressure, without sunlight, then maybe life is everywhere. Maybe biology is not a miracle, but a pattern, a thread that runs through the fabric of the cosmos. Even on Mars, the red planet, there are hints. Ancient riverbeds, polar ice caps, traces of methane in the air, a past that may have once been warm, wet, and alive. Robotic explorers crawl its surface now, drilling, analyzing, searching, not just for curiosity, but for connection, to know whether Earth is unique or simply one chapter in a much larger story. Black holes are often seen as the end, the final stage of stellar collapse, a place where even light cannot escape. But in truth, they may be something more, something stranger. At their heart lies a singularity, a point of infinite density where the laws of physics as we know them break down. Space and time themselves curve inward toward this point, like water spiraling down a drain. But some theories suggest what lies beyond isn't a void, but a bridge, a wormhole, a doorway to another place, or another universe. These ideas remain speculative, but tantalizing. In the universe's deepest pits, we may find not destruction, but connection. And yet, black holes don't just consume, they shape galaxies. The one at the center of the Milky Way, silent and immense, may regulate the birth of stars through its gravitational pull. In a strange irony, the very things that destroy light may also give structure to the galaxies that cradle it. They are not simply cosmic monsters, they are architects of the cosmos. As we observe the universe, we are not just looking out into space, we are looking back in time. Because light has a finite speed, every star we see is a snapshot from the past. The moon is 1.3 seconds away, the sun 8 minutes, the nearest star over 4 years. The Andromeda galaxy, 2.5 million years. When we gaze into the night sky, we are reading ancient messages, light that has traveled across unimaginable distances to meet our eyes. A galaxy seen at 13 billion light years away is a glimpse of the infant universe, when the first stars were just beginning to shine. And those first stars were unlike anything we know. They were giants, massive, short-lived, and made only of hydrogen and helium. Born in a time before carbon, oxygen, or iron, these primordial stars burned hot and died fast, seeding the cosmos with the first heavy elements. From their ashes, later generations of stars emerged, and with them, planets, moons, and eventually, us. Every atom in your body was once inside a star. You are not just in the universe, you are of it. We dream of faster-than-light travel, of starships, warp drives, wormholes. And while current physics forbids it, some concepts push the boundaries. The Alcubierre drive, a theoretical model, proposes bending space around a ship, compressing space in front and expanding it behind. The ship itself never moves faster than light, but the space around it does. It's speculative, unproven, and would require negative energy, something we've never seen. But it represents the essence of exploration, the desire to go beyond what's known, to chase the horizon. And there is no horizon more daunting than time. What happens to the universe in the far future? The galaxies will continue to drift apart. Star formation will slow. The stars will age, dim, and die. White dwarfs will cool. Black holes will evaporate through Hawking radiation. Over trillions, then quadrillions, then quintillions of years, everything we know will fade. Matter itself may decay. What remains is the heat death, a state of maximum entropy where no energy flows, no stars shine, and the universe becomes cold, dark, and still. But perhaps that is not the end. Some physicists believe that even then, new universes may emerge, that black holes could give birth to new big bangs, that our universe is just one in a cycle of births and deaths, a pulse of cosmic breath on a scale beyond comprehension. Or maybe we are a quantum accident, a fluctuation in a greater multiverse, a bubble of order in an ocean of chaos. And still, we look up. With telescopes on mountaintops and satellites in orbit, we scan the heavens. We listen for radio signals. We model alien climates. We ask questions no other known species has ever asked. We are curiosity incarnate, a flicker of awareness in a sea of stars. We build machines like the James Webb Space Telescope to see the first galaxies. We design rovers to crawl across alien dust. We train AI to analyze starlight, hoping to detect the breath of life on distant worlds. Because maybe we are not alone. Across the void, in the spaces between stars, we've been asking a question older than our species. Are we alone? For over half a century, we've been listening. Giant radio dishes point toward the stars, scanning for artificial signals, patterns, pulses, mathematical structures that nature doesn't make. We've heard only silence, but the silence is not proof of solitude. It may simply be the distance between civilizations, or the briefness of their existence, or the strangeness of their language. A message could be streaming through us right now, encoded in a frequency we don't yet understand. Life, as we know it, requires liquid water, organic molecules, energy. But we found these ingredients in surprising places. Beneath the ice of Jupiter's moon Europa, in the methane lakes of Saturn's Titan, in ancient Martian riverbeds. If life can arise in one place, it may arise in many, and it may not resemble us at all. On Earth, life has adapted to boiling vents, freezing poles, crushing pressure, and acidic swamps. Life is resilient, adaptable, creative. Perhaps the universe is too. Some scientists believe microbial life could exist now, hidden in alien oceans, or clinging to the clouds of Venus. Others look to distant exoplanets, thousands of them, orbiting distant suns. We've found rocky worlds in habitable zones, some with atmospheres, some with strange chemistry. We've even started to detect biosignatures, hints of gases that, on Earth, would suggest life. Nothing confirmed, but enough to keep asking, enough to keep hoping. And then there is the Fermi paradox. If the universe is so vast, so old, so full of planets, where is everyone? One answer may be distance, another, time. Civilizations may rise and fall like sparks in the dark, too brief to overlap. Or maybe the intelligent ones don't broadcast. Maybe they watch in silence, or hide, or evolve into something we wouldn't recognize. Perhaps consciousness itself is rare, or fleeting, or self-limiting. But what if they're out there, old, wise, ancient beyond imagination? Would we even recognize their presence? Would their technology bend space, harness stars, manipulate matter at the quantum level? Would they build Dyson spheres, vast structures around stars to capture energy? Would they live in simulations, abandoning physical form? Or would they be simple, biological, curious, like us, searching the stars for signs of company? In 1974, we sent the Arecibo message. A radio signal beamed into space toward a globular cluster 25,000 light years away. It contained information about our species, our DNA, our solar system. It was symbolic, more art than outreach. But it marked something profound. The moment we said hello, knowing we might never hear back, knowing the odds. We sent the message anyway. If we ever do make contact, what then? Will we understand each other? Will it be a moment of awe or fear? Will we see in them a mirror of our potential or a warning of our limits? The first alien signal will be the most important discovery in human history, not because it tells us who they are, but because it confirms we are not the only question the universe has asked. And if we never hear from anyone else, then that means something too. It means intelligence is rare. It means life is precious. It means, for now, we are the only known voice in the cosmic dark. And that voice matters more than we thought. Because whether or not we find others, we have already found each other. And we have the tools, the mind, the vision to keep reaching. The stars have always called to us. For most of human history, they were myth and mystery, painted on the night sky like stories we could never touch. But now, for the first time, we stand at the threshold. The tools we build are no longer just for looking up. They are for leaving. Rockets break the grip of Earth's gravity. Rovers crawl across distant worlds. Space stations orbit above us. Fragile outposts of life in a place where no life belongs. We are learning, slowly, cautiously, but inevitably. Still, the stars are far. The closest one, Proxima Centauri, is over 4 light years away. With current technology, it would take tens of thousands of years to get there. But we are dreamers, and we are builders. Projects like Breakthrough Starshot imagine tiny light sails pushed by lasers, miniature ships traveling at 20% the speed of light. Others dream of fusion drives, antimatter propulsion, or even warp bubbles, theoretical ways to cheat distance by folding space itself. These are not science fiction fantasies. They are ideas in development, blueprints waiting for breakthroughs. To live among the stars, we must change, not just our machines, but ourselves. On long interstellar journeys, generations may live and die aboard ships. Some speak of cryogenic sleep, others of digital consciousness, uploading the mind into data, sending ourselves as information rather than flesh. And if we reach distant planets, we may not remain human as we are now. We may become something new, adapted, engineered, interwoven with AI, shaped by alien gravity, alien air, alien light. But before we go far, we must go nearby. The moon is our testing ground, close enough to reach, harsh enough to teach. We will build there, habitats shielded beneath regolith, solar farms capturing endless sunlight, laboratories studying how life copes with barren rock, And then Mars, a world with winds and seasons and canyons deeper than any on Earth. We'll send crews, then settlers, then children born under a pink sky. They will not remember Earth the way we do. To them, it will be the myth. Terraforming may come next. Vast projects to warm planets, thicken atmospheres, release water. It could take centuries, millennia. But we've changed Earth accidentally in a few short generations. Given time and will, we could sculpt other worlds deliberately. Mars, Titan, even the moons of Jupiter could one day be wrapped in domes, crisscrossed with greenhouses, seeded with life. Not just to escape Earth, but to spread it, to become a life-bearing force in the galaxy. And what of Earth itself? We must protect it, not only because it is our home, but because it is rare. So far, we have found no other place like it. If we ruin it, we may not get another. If we save it, it can remain our root, our memory, our origin story. A pale blue dot that birthed a species capable of dreaming far beyond its sky. As we grow, we may form a civilization that spans planets, moons, eventually stars. A Type 1 civilization, mastering the energy of a world. A Type 2, harnessing the full power of a star. A Type 3, commanding the energy of an entire galaxy. These are not tomorrow's goals, but they are not fantasy either. If we survive, if we cooperate, innovate, and endure, the stars are not the limit. They are the beginning. Artificial intelligence may be our partner in this, or our successor. Machines that think faster than us, build smarter than us, learn beyond us. They may one day run starships, build cities on Europa, mine asteroids, terraform planets. They may teach us things we cannot imagine, or carry our legacy if we fall. And if intelligence evolves in the galaxy more than once, it may not always be biological. The future of thought may be silicon or quantum, or something we do not yet have words for. We are at the very start of this journey. A species only 300,000 years old. A civilization barely 6,000. A spacefaring race just 60. We are children with fire, building towers to reach the sky, asking ancient questions with new tools. We will make mistakes. We will fall. But if we rise again, and again, the universe will open. And what waits out there? New physics, new life, new challenges, new beauty. Maybe we will meet others. Maybe we will outlast the stars. Maybe we will become the stars, burning with knowledge, scattered across the galaxy, eternal in light, if not in form. Because the true story of space is not distance. It is not silence. It is potential. And the greatest chapter may still lie ahead, written not in stardust, but in the minds of those who dare to reach beyond everything they've ever known. Eventually, the stars will go dark. One by one, their fuel will run out. The great engines of the cosmos, forged from gravity and hydrogen, will sputter and die. Red dwarfs will linger, glowing dimly for trillions of years, the last to fade. But even they will succumb. In the far future, the universe will enter its degenerate era, an age of ash and ember, where white dwarfs, neutron stars, and black holes are all that remain. No new stars will be born. No new light will emerge. The galaxies will be cold, quiet ruins drifting in a void grown unimaginably vast. Black holes will dominate. They will continue to consume, to merge, to grow. And then, even they will begin to vanish. Slowly evaporating through Hawking radiation, they will release their mass as a trickle of particles into the dark. The largest will take a Google years to fade, a number with 100 zeros. And when the last one disappears, there will be nothing left that shines. No matter, no motion, no heat. Only particles spread so thin they may never touch again. This is the heat death, not fire, but stillness. Entropy maximized. A universe where everything has happened and nothing remains to happen. No gradients, no energy to harness, no change. It is a state not of destruction, but of final equilibrium. It is the end of all stories told in matter and time. And yet, some theorize this may not be the final end, that quantum fluctuations may create new universes, bubbles of order in the sea of stillness. Some may grow, inflate, ignite into new spacetimes with their own physical laws. Perhaps ours was born this way. Perhaps the multiverse is real, an endless fractal of beginnings, each unaware of the others, each infinite in its own right. Some suggest our universe may be a simulation, not a metaphor, but literal code, running on a substrate we cannot perceive. That everything we know, stars, planets, consciousness, is emergent behavior within a deeper reality. The simulation hypothesis posits that advanced civilizations could create entire worlds indistinguishable from base reality. And if they could, they likely would. And if they would, we may be inside one now. But even if that is true, it changes nothing. The stars still burn, the void still stretches, the questions still matter. Whether written in carbon or code, we are here, experiencing, wondering, becoming. Consciousness, the strangest force in the universe, may be its most powerful. It can't be weighed, it can't be seen. Yet it shapes civilizations, tells stories, asks questions, feels awe. From the structure of neurons to the fabric of space-time, we are finding connections. The brain and the cosmos, both networks, both pulsing with information. Some believe consciousness is fundamental, woven into the universe like space and time. Others see it as an emergent property. The brain, a temporary mirror held up to the infinite. And still the mirror reflects. Still we wonder. Still we reach. No other creature we know of has ever looked up and asked why. No other planet, as far as we can tell, has grown eyes to see the stars. That may change, or it may not. But for now, in this moment, we are here. A flicker of thought on a grain of dust, orbiting a small star in a quiet corner of a vast and ancient galaxy. And that, against all odds, may be enough. In the deep architecture of the cosmos, patterns repeat. Spiral galaxies mirror the whirlpools in our oceans. The filaments of the cosmic web resemble the neural pathways of the brain. The golden ratio appears in the arms of galaxies, in the growth of seashells, in the branching of trees. The universe, in its vastness, echoes itself, from the micro to the macro, from the subatomic to the galactic. These patterns are not proof of design, but signs of underlying order. Structure in chaos, law in the unknown. The universe is not uniform. It is lumpy, uneven. Galaxies clump together in webs, connected by filaments of dark matter, separated by vast voids where almost nothing exists. These cosmic voids are hundreds of millions of light years across, expanses so empty that a single galaxy passing through would be like a grain of sand in the Pacific Ocean. And yet, even here, gravity whispers. Even here, expansion continues. Quantum mechanics tells us the universe is not made of things, but of probabilities. Particles blink in and out of existence. Locations are uncertain until measured. Entanglement links particles across space, instantaneously, as if the universe itself does not care about distance. Reality, at its core, is fuzzy. The closer we look, the less solid it becomes. And yet, out of that uncertainty emerges everything: matter, energy, time, thought. There are particles that can pass through entire planets without slowing down. Neutrinos, ghost particles, are created in nuclear reactions, in the hearts of stars, in supernovae. Trillions pass through your body every second, unnoticed. They are messengers from the core of suns, from the edge of the universe, from moments after the Big Bang. They are the silent threads connecting us to everything. There are places where time moves differently. Near black holes, seconds stretch into hours. In accelerating frames, clocks run slower. This is not illusion. It is the shape of reality. A traveler moving near the speed of light could journey across the galaxy and return to find centuries passed at home. Time is not fixed. It bends, warps, flows. It is part of space, and space is not a backdrop. It is alive, shifting, reactive. The universe is not a stage, but a player. And perhaps the strangest truth of all, the universe has no center, no edge, no outside. It is not expanding into anything. Space itself is expanding, everywhere, all at once. Every galaxy sees every other galaxy moving away. The fabric is stretching, the scale is growing, and yet, from inside it feels still. Motion without movement, infinity without direction. The laws of physics are not merely descriptions. They are constraints, but also keys. They allow life to emerge, stars to burn, atoms to bond, minds to think. And they are, as far as we know, the same everywhere. The same on Earth as in galaxies 10 billion light-years away. This uniformity suggests a common origin, a singular birth, a moment when all things began, hot, dense, bright, and then expanded, cooled, evolved. And yet, even now, the universe is not done becoming. Stars are still born, galaxies still collide, planets still form. Somewhere, right now, a world is cooling from fire into stone. Somewhere, right now, life may be waking up for the first time, crawling from the sea, gazing at its own sun, wondering. Somewhere, right now, a civilization may be transmitting its first signal. Somewhere, right now, we may be the signal they're hearing. Because this is not just a story of stars. It is a story of time, of emergence, of consciousness finding itself in the mirror of space. The universe does not explain us. We explain the universe, and in doing so, we give it meaning. The universe is not static. It is not a finished canvas, but a work still in progress. A slow, unfolding act of creation, playing out on a timescale so vast we can only catch fragments. In every supernova, in every merging galaxy, in every newborn star, the story continues. It is a cosmos in motion, not drifting aimlessly, but evolving, shaped by laws we barely understand, into forms we can barely imagine. Between the atoms in your hand is empty space, vast and silent, proportionally as empty as the distances between stars. The solidity of matter is an illusion of quantum fields and electromagnetic forces. You are not made of things, but of relationships, interactions, fields vibrating into what we call matter. And yet, from this emptiness emerges thought, memory, love, a mind aware of itself, looking outward and inward all at once. Your body is made of hydrogen from the Big Bang, carbon from dying stars, calcium from ancient supernovae. You are the dust of collapsed suns, organized by DNA, into a form that can ponder its own origins. Life is the universe folding in on itself, a pattern of molecules complex enough to ask why. This is not philosophy, this is physics. Every breath you take is shared with the past. The oxygen in your lungs may have passed through the leaves of trees that grew before you were born. The water in your veins may have once flowed through ancient rivers, ancient animals, ancient storms. You are not separate from the Earth, and Earth is not separate from the cosmos. It is a vessel, a temporary concentration of matter and energy, forged by a billion accidents and a few consistent laws. And still, there is so much we do not know. We do not know what dark matter is. We do not know why there is more matter than antimatter. We do not know how consciousness arises from tissue, or if it even does. We do not know if the constants of nature are truly constant. We do not know if time had a beginning, or if it loops, echoes, branches into infinite paths. We do not know how the universe will end, but we know that everything that begins also changes, that all structures, all stars, all thoughts are temporary, that impermanence is not failure, but nature. The arrow of time moves in one direction, driven by entropy, the tendency of systems to move from order to disorder. And yet within that law, pockets of complexity emerge. Galaxies, solar systems, life. This is the paradox. The same universe that trends towards simplicity also gives rise to stars, cells, minds. The same randomness that scatters also creates. It is within this tension, between chaos and order, that life finds its window. It is here that meaning is born, not from design, but from participation, from existence itself. You are not separate from the cosmos. You are a way for it to feel, to ask, to wonder. A brief arrangement of particles tuned by time into awareness. And as you look out at the stars look back through you, because for a moment, in this tiny corner of space, the universe knows that it is vast, and it knows that it is beautiful. There is a silence in space that is absolute. It is not quietness as we know it, but the absence of medium, the absence of air. Sound cannot travel there, and yet the cosmos speaks. It speaks in light, in radiation, in gravity. The collision of neutron stars sends ripples through space-time, gravitational waves that stretch and squeeze reality itself. We have built instruments so sensitive they can detect these ripples from galaxies millions of light years away. With them, we listen not with ears, but with mathematics. We hear the universe through distortion. And in that distortion, we find new truths. Space is not smooth. It is not flat. It curves around mass. It twists near spin. It dances under tension. It expands. It vibrates. It bends. It is not the stage upon which the universe acts. It is part of the cast. It interacts. It flexes. It remembers. Black holes may be the ultimate memory, not just devourers, but recorders. According to quantum theory, information cannot be destroyed, and yet black holes seem to swallow it forever. This contradiction between relativity and quantum mechanics is one of the greatest puzzles in physics. Some believe that information is encoded on the event horizon, like a hologram. Others believe it leaks out in Hawking radiation, twisted beyond recognition. Others still think our understanding is too limited, that something deeper awaits discovery. A new theory, uniting gravity and quantum mechanics at last. That theory may not just explain the universe. It may explain everything, why there is something rather than nothing, why the laws of physics take the form they do, why the cosmos permits life, thought, love. We call it the theory of everything, and we have not found it yet. But every equation, every telescope, every experiment brings us one step closer to unveiling the machinery beneath the veil. In all directions, the universe looks the same. No matter where we point our instruments, we see galaxies drifting away, redshifted by expansion. This symmetry suggests something astonishing. There is no preferred place, no center, no edge. Every point in space sees the same outward motion. We are not in a special location. We are not above or below. We are not central. We are simply within, embedded, carried by the flow. And yet, for all its indifference, the universe has given rise to meaning. Not absolute, not universal, but emergent. Meaning is not written into the stars. It is written into minds. It is what arises when consciousness collides with time. We invent it. We suffer for it. We live by it. And in doing so, we become something greater than matter. We become participants in the unfolding of a reality that did not ask for us, but allowed us anyway. The universe does not owe us comfort. It offers no guarantees, no protection, no permanence. But it permits us. It permits stars to form. It permits chemistry to dance. It permits biology to emerge. It permits atoms to arrange themselves into minds that can imagine futures, remember pasts, and build tools to reach beyond what is visible. That permission, that fragile, narrow band of possibility, is everything. And though we are small, we are not powerless. Though we are brief, we are not irrelevant. We are, perhaps, the only voice the universe has ever had. A single point of awareness in a sea of silence. But a point that burns, that questions, that dreams. A point that, even knowing its own impermanence, still dares to reach for the stars.